frequency amplitude will also decrease. So this is a problem. We cannot decrease too much. And if we are keeping high, this line width will be power broadened. Okay. So can we do something different? An answer is yes, we can do something different. And we can do some homodyne detection of two-photon resonance. Okay, now this, this interferometric method is quite useful in determining the even small variation of the phase and all. So we can use the same technique to determine the two-photon resonance condition. And how can we do it? So I'm saying homodyne detection. First of all, what is homodyne detection? It is very well-known experiment. It is similar to Michelson interferometry experiment, where a beam is splitted into two parts, okay, and then it is recombined at a photodiode. One path is going through some perturbation, and then one is not. So we can easily make out what kind of perturbation is created here. This is very well known, and this figure is from Wikipedia. So now, in our case, we are having two sources of light. One is flash. Okay, I will explain what is flash. And another one is slow light. So in this arm, there is slow light you can consider. And in another arm, there is a flash. What is flash and what is slow light? So in order to describe flash, I go to very, ordinary topic. I mean, very well-known subject. That if we shine laser, okay, on a opaque medium, okay, or on a sample where atoms are there, there is going to be a reduction in the intensity. Okay, this is well-known law that is called Beer-Lambert law. The question is how this reduction happens, why this intensity is decreased. I'm going to tell you something different. Okay, I say that there is an incident light, and then this light comes, and then these individual atoms are like a dipole. So then in the presence of this electric field, incident electric field, this dipole are going to oscillate and gives rise to a scattered field. And then this scattered field and incident field, they interfere destructively. At resonance, they interfere destructively, and then hence we get the transmitted beam happens to be very, very small. We have to convince ourselves that is it really destructive? So I will say that the phase of the incident field and its scattered field will be pi. And we know this one, that if this is the dipole and then there is incident field, at resonance, the phase of this oscillating dipole will be given by this quantity. And at resonance, this phase will be pi by 2. So this oscillating dipole will be oscillating with a phase of pi by 2. But there is another going to be a pi by 2 phase, and that's called GUI phase. For long distance, this scattered field picks up an extra pi by 2 phase, and we are having a pi phase. So at resonance, we are convinced that there is going to be a destructive interference between the incident field and scattered field. Okay. Now, how fast this dipole can respond? So for example, if we shine very, very fast and switch off the light, it is not going to respond. This dipole is not going to respond at all. So what is the response time of dipole is determined by the gamma, where gamma is the damping rate in the classical picture, if you want to say, or in classical picture, if you want to say that this is a decay time. So now it helps us to understand the flash. Further, one more thing, that scatterers, this scatterer and this scatterer are going to be coherent in the forward direction because there is not going to be a phase picked up. While in any other direction, there is going to be a phase. So in the forward direction, these scatterers act cooperatively. So these are the two key points. First point is there is going to be out of phase. The scattered field will be out of phase. And in the forward direction, all the scattered field will be add up coherently. So let's understand this flash. So if we sign a square pulse, okay, here. So if at the rising slope, this scattered field has not been built up because it takes some time to build up. So just at the rising slope of this square incident pulse, we are going to see some flash of light, okay, momentarily. Slowly flash, the coherent scattered field build up, and then they interfere destructively, and then we see the medium to be opaque here. Again, if we suddenly switch off the incident field, the scattered field will not die immediately. It will take some time. Okay. And even though incident field is not there, only scattered field will be there. So for a moment, there is going to be a flash of light, and this is called flash. Okay. But we have to switch off very fast compared to the lifetime of the excited state. Now we understand what is flash. The other source which I was talking about, taking part in this interference, homodyne interference, is slow light. What is slow light? If we take the lambda system in the presence of control laser, this probe laser is going to be transparent for the absorption. That is due to the modification of the refractive index for the imaginary part. But there is going to be a modification in the refractive index, and there is going to be a huge slope in the refractive index versus detuning or frequency. And that's why we see a slowing of light. It's very common, and the slowing of light has been demonstrated. It has been demonstrated up to like 20 meters per second. So this is the slowing. The slow time is given by this quantity. Okay. So we are aware now that there are two parts. One is the flash, and another is the slow light. So how much time I have spent already? Can you guide me?
Yes, another 5 minutes before, actually, in fact, you have another 10 minutes before we take the questions.
Okay, that's very good. Okay. So now we are having two sources of light which are going to interfere. So this part, you see, as I told you that this part is slow light, and then phase of this slow light is determined by the detuning, 2-photon detuning. So basically, what we are going to do is, if we are wiring the detuning, means 2-photon detuning, there is going to be a change in the phase of the slow light. The phase of this flash is fixed because we are very much near to the resonance. So we are changing the phase, and it is acting as a Michelson interferometer. The position of the bright fringe is given by this quantity, where m is the odd integer. And you see that line width now is given by this quantity. Here, the first maxima we are seeing is omega square by beta, while regular case we see as a square root b. So we can reduce the line width of this EIT deep in this transient regime using this interferometric technique by huge amount. It depends upon what is the optical thickness we are having. So typically optical thickness we can have is 50, 100, in fact, okay, even 200. And that's why we want to increase the optical thickness. And that's why we started cooling and trapping of rubidium at narrow transition, because it can give better optical thickness. So let's now talk about cooling and trapping of rubidium. So this is the very commonly used energy level, which is used for cooling and trapping of rubidium. Typically, temperature in this rubidium mott we get is like 200 microkelvin without subdoppler cooling. Well, I mean, you can say that subdoppler cooling reduces temperature, but at same times, you know, we have to give like 3 to 5 millisecond time of flight for subdoppler cooling, and by that time, cloud expanded. So this is not which we want. Okay, we do not want the cloud to expand and then optical thickness goes down. Okay, so what we do is we decided to do the cooling and trapping of rubidium at narrow transition. And here is the complication now. Here is the regular cooling and trapping mechanism. And here we are exploring another one, that is narrow transition. Okay. And there is branching also. Okay, it doesn't decay back to this ground state, while this one is closed transition, while this one is not. So we are also not sure that subdoppler cooling mechanism is going to work at blue transition or not. But let's see. We have to do the experiment and see how it is going to work. But certainly in the magneto-optical trap, it will be, the temperature will be lower, and the temperature will be lower by 5 times. So in mott itself, we are expecting to have a temperature 40 microkelvin, which we generally get with a large number of atoms in rubidium after Doppler cooling. Since this transition is narrow, the spectroscopy of this transition is very difficult. Okay. For that, you have to do heating of the cell and so on. There is going to be a coating. So we were troubled a lot by this heating of the cell. So we went for another transition. Okay, another method of doing this double resonance, that is called double resonance, where we monitor the probe absorption at 780 in the presence of 420. And because this transition is not closed, we are going to see the transparency when this control is scanning and coming to the resonance. Similarly, when there is going to be a this transition here, we are going to see increased absorption. And we have recorded this absorption, and signal is quite good. Signal to noise ratio is very good. Or in fact, we have done the precision measurement where, you know, it's good to talk here about this precision measurement, because Professor B.P. Das group is very much active on this kind of calculations. So we have done this measurement up to 400 kilohertz precision. And then we came to know that there is some recent paper coming out on the archive, and they have done the measurement with frequency cone, but they have measured the absolute frequency, and then precision is almost similar. What is the limitation of this double resonance? The double resonance limitation is the Doppler mismatch. You know, this double resonance works very well if you are having probe and control having same kind of wavelength. But here we are very much different. One is 780 and 420. So Doppler mismatch cause broadening. So the typical line width we are getting is like 30 to 35 megahertz, while natural line width which we expect is like 7 to 8 megahertz. And that's big problem. So what we came with another idea is we talked about velocity-induced coherent population oscillation. So where we are assigning, okay, two more counter-propagating laser, okay, and since the atom is moving in the atomic frame, the atom is seeing a beating of two lasers. In the rest frame, the frequency is even frequency is same, but in moving frame, the atoms are beating. And the response of this beating is only limited to the natural line width. As I told you, that the response of the dipole, the response time of the dipole is within the natural line width. So this, if we do like this, we will be able to extract the information of the atoms which are moving in the velocity range, which causes the Doppler shift close to the line width. Okay, and that is the key. So using this method, we did the spectroscopy, and then we got the line width close to 9 megahertz, which is very much encouraging. In fact, we were able to resolve the closely spaced levels, okay, which we were not possible to resolve if we are using this 2-photon resonance like this. So we assign a counter-propagating blue laser and then counter-propagating red laser, and you see that this blue curve, the red curve is corresponding to this energy level, and then green curve is corresponding to this. So we were able to resolve these two closely spaced hyperfine levels. So now we resolved, we did the spectroscopy. In fact, we locked the laser before lockdown. We locked down this laser, the transition. And now we are ready for the cooling. Well, we are having only one 420 nanometer laser. So we are using the repumper at 780, and let's see whether cooling works. Okay, you can argue that, hey, come on, the repumper is still there, which might heat up. But if the branching is good, we can expect that lowering of the temperature. If experiment is not successful, we have to sign another blue here. But we are hopeful that branching we have checked, and we are hopeful that there is going to be reduction of the temperature. So we have done the cooling and trapping of rubidium. Here is our cell. First, we did the cooling using 780 regular cooling and trapping of MOT. And then we got, here is the setup. And then we got this 780 magneto-optical trap. Loading rate is good. And then even, okay, so also we do not have camera, and also once camera will be installed, we will be able to know how many number of atoms are there. But those who are working in the field, if by the experience, if they can see the MOT with naked eyes, it means that we are on the right track. So we are able to see with naked eyes very, very good MOT. So we are on the good track. But ultimately we have to install the camera. So we continued cooling the MOT with 420. So in order to cool, first trap the rubidium MOT with 780, and then we switch off the 780, and then the atoms will be trapped. Here, this is a combination of 420 MOT and red MOT. What we did is, in one arm we didn't have 780, but we signed just blue, and then we were able to trap the atoms. And here is the final slide. So here we are having folding time. So if we are not having any 420 nanometer laser, we are not. So here first we trap the 780 MOT, and then we switch off 780 nanometer laser, and then again switch on. So we switch on after 100 milliseconds. So if 420 is not there, we can't see immediate buildup of fluorescence. If 420 MOT is there, we can see here immediate buildup. So it is, so in this indirect method, we are able to show that there is 420 nanometer laser. So this is one day before this lockdown happened in our institute, and we are still in the process of characterization. I would like to thank my collaborator and the group member at IIT Guwahati. This Chetan Sriram, he was UG here, and then he is doing PhD with David Wilkowski. And we are also having a lot of collaboration with Professor Vasan. Thank you very much.
Thank you, Dr. Pandey, for the nice talk. Okay, there are a couple of questions. So can I take it now?
Yeah, sure.
This is from Saurav. 920 nanometer plus 780 nanometer should ionize the atom. How does it affect the mode?
Yeah, so basically we do not we are careful about it, and we do not sign this. Yeah, so basically we are not seeing any kind of ionization happening. Okay, that is very good point. And still,
how do you know that it's not happening?
So the mode is there.
Yeah, but you could be losing atoms. You're just not detecting it. So if you put a detector,
well, that similar method has been implemented with potassium, and they do not report this problem. So repumper we keep while making mode, but mode beam we switch off. In fact, we were also worried about this problem, but we said that let's go ahead, and since they have already implemented with potassium, we should be checking it.
Okay.
Any other questions? Apparently, there is no question from the YouTube, so we will open. We have a couple of more minutes. If you have any questions, we can please take it up.
In fact, we were more worried about in the spectroscopy process itself that what will happen if it ionizes. And then we go ahead and did the spectroscopy. It was coming to be okay. And then we go ahead making mode.
Yeah. Okay.
Okay. Thank you. So since there is no more questions, let's thank again Dr. Pandey for this wonderful talk. And let us move to the last talk of the morning section. This is by Dr. Bodhaditya Sandra. He is affiliated to the Department of Physics, Indian Institute of Technology, Delhi, IIT Delhi. He will be talking on the cold atom toolbox from fundamental physics to quantum computing. Dr. Sandra, can you hear me?
Yes. Can you also hear me?
Yes, I can hear you. I can also see you. Can you please load your talk so that I'll just make sure that it is all visible before I sign off.
Thank you. So it says that I cannot start my screen until others.
Can you please stop sharing?
Please, Sanjay, please close your presentation.
Okay, maybe now I would be able to.
Sorry, not Sanjay, Pandey. Dr. Pandey, please close your presentation. Yeah, I think he has done this. You try now.
Yes, I'm trying. It's not yet shared, right?
You may have to share it.
Yes, I'm doing
Share
it.
screen.
Share screen.
So there will be a bottom on the below somewhere bottom line. There will be a panel.
Yeah.
There will be a green color share screen.
Yes, I'm doing that. So
okay.
My computer is asking for some permission.
Yeah. So ask. Okay. Say share. So it will be asking many.
It's asking
options.
to zoom to allow. So I'm giving it.
Yeah. You do that.
Yeah,
yes.
You allow it.
I did that. Just a moment. Let me do it again. Sometimes there is a conflict with Mac. I hope it will work soon. Zoom. Okay. Yeah, I hope now this will work. It seems like I have to quit once. Okay.
Yeah, just please quit and log in again.
Yeah.
Sometime works that.
So Binjay, can you call Bodho and instruct him what to do?
Yeah, yeah, I'll do that. Yeah,
Yes, I think, yeah,
yeah.
you can see the screen. Now you can zoom it up the full screen. Yes, that's good. That's good. Wonderful. Hello.
Okay, sorry, my video and the sound was muted. So I hope you can
Yeah,
hear.
now I can hear you.
Okay.
So you have 25 minutes plus 5 minutes for questions. So at the end of 20 minutes, I'll just give you a small time.
Okay, thank you very much. So
Yeah,
sorry
so
for this.
I will now hand over to you. I will mute my both mic and this.
Okay, okay. So
Over to
sorry
you.
for this. So
No
thank you.
problem. No problem.
So yeah, I'd
Please
like to
go ahead.
thank organizers a lot, and also the chair, Professor Pai. So it was always, when we meet, it's very nice discussions, and especially with Professor Bhanudas. I mean, it's a, I think now developed a different level of relationship. It's not up to the scientific collaboration. So I would present. I do not.
ID password of everything and WhatsApp, because Bishop wants to enter and he has lost all the information. He wants in WhatsApp because I'm not able to copy the password, that ID and password from my Zoom. Oh, sorry. Oh.
So yeah, so actually I would I do not have some pictures with him, but I do have some very good memories, and also the reason why I get in touch with him, I will show some results in honor to him. But just for starting, so today actually I'll be talking about what we could have using ultra cold or cold atoms in general. This is really a versatile field with lots of different kinds of precision knobs to tune various parameters. That's why it became an interesting platform for studying fundamental physics and also going to quantum technology. So quantum computing is a buzzword, but there are many other kinds of quantum technologies, starting from quantum sensing, quantum communication, and quantum simulations. So the work I'm going to present today, these are development over a really long time. So I'm already starting from my PhD. So in University of Groningen, University of Kaiserslautern, University of Hamburg, and then University of Innsbruck, and then some updates about what we are doing now. So just to give an idea, like and a motivation. So why would we need to care about quantum technology? So how does it influence? So we should not do it just for the sake of doing it. There should be a very good and well-defined need for it, right? And so some of the possible reasons are like if we have, just imagine electrical cables which has very low resistivity. Just from practical point of view, we have to pay less, and we can also kind of make a very good use of this nature's resource. And also this thing had also long consequence in even in climate changes, things like that. and making materials like a smarter and smaller and compact. I mean, the reason why we are having so much good mobile phones these days is just due to because of the advancement of this smart material fields. In the regime of drug design, I mean, nowadays we do not have to tell anybody what is the importance of drug design, and these things also requires many combinations and many permutations between different kinds of molecules, what kind of reactions are taking place. So drugs are not more than some molecules, right? Or maybe a chain of molecules. And then going to a little bit more applied kind of things. So optimization problems. So there are different kinds of optimization problems. It could be from flight route directions to maybe mobile tower placings. So that's the optimization is more or less everywhere. And then comes the secure communication. So all this banking industry and many other places where the confidentiality has to be maintained there. So the communication should be very, very secure. So how to do that? So and then like modeling Earth. So like there are many natural hazards starting from earthquake and tsunamis and many other things. So and also for natural resource findings. So if we have a very good sensors which could perform better than the sensors we have in today's date, then that would be really great. And it seems like the sensors what we could build using like quantum objects can play a big and good role. And cold atom is also providing one of the very good state-of-the-art system in that region. And now going to like, yeah, of course, what I told you, these are some of the problems, some of the places where we could gain using quantum technology. So what can we do using cold atoms? So like the first, this top row left picture, what you see, this is an picture from a quantum gas microscope where like these lithium atoms were trapped. So basically this is an arrangement in an antiferromagnetic order. And if you look into the phase diagram of this antiferromagnetic order, then you see at some point towards the lower part of this phase diagram, there is the superconductivity. So using these modern systems, we could really learn about like how to go to those phases. And this type of information helps us in building the real materials. So, and now if we know how to get to these superconducting phases, then we could also build the materials which can behave as a superconductor. And now getting these superconductors working at a room temperature would be very, very useful. So other topic is other type of problem is the topological properties. So we know that there are many important work is going on about quantum computing, and one of the biggest challenges the environmental decoherence. And now if you could encode the qubit into kind of not into a geometrical property, but into a topological property of a quantum system, then this system would not be that much prone to the like environmental perturbations. So that's one of the important reasons why studying topological properties of various type of systems are important. And in Hamburg, actually, we are studying what is the type of topological phases we could have if we load fermionic atoms into a honeycomb lattice or a triangular lattice. Actually, both of them have same basis as a hexagonal. Okay, and then comes this molecule. So basically in our field, so we could basically trap two single atoms, combine them, and then we can form molecule. I mean, in the first glance, it sounds very simple. I mean, what can you do with that? But already, if you look into the, or even think into the level structure of a single atom, and when you combine two such single atoms, the electronic structure is quite complex. So, and you know, we have to start with the simplest thing to develop the concept. So that's why these things also provides a very good kind of a platform for understanding them. And definitely this understanding would help us in developing knowledge about how to approach for more and more complex molecules. And in the bottom there you see on the very left side, so these are an array of basically defect-free array of neutral atoms, so single neutral atoms. So if you have an array of single neutral atoms or ions or any quantum object, then you could use each of these single objects as a qubit, because it has several internal states. And now if you can have a really large number of these arrays, or these qubits, then this could play an important role in exploring like a large scale quantum computer. What do we need for solving the real world problems? Of course, it will take long time, but we have to go step by step. And I think this is one of the very first step from the cold atoms point of view. And then for the quantum communication, there are many, maybe not too many, but at least a sizable fraction of experiment which showed if you put these atoms into cavity, or even if you put atoms in the very close to the like a tapered fiber, so basically you can trap these atoms into the evanescent wave, then you can make a very efficient like a light photon, so atom photon interface, where you can kind of exchange the information from a like the static qubit, which is an atom, and to a flying qubit, which is a photon, which you can then transport over a long distance. And then this optical lattice clocks, I mean, these are the best devices for measuring any frequency. So they can be used for any kind of quantum sensing, or they have many other applications, but also for quantum sensing, and which is not in this slide. So there are not many things which are not in this slide. So for example, this atom interferometers, they are also very good quantum sensors, solely made with atom clouds. Okay, so the outline of my talk would be the following. So I would talk a little bit about the precision spectroscopy of 225 radium, and then talking about optical lattice clocks. So basically, I would like to show some things what normally is not shown into the paper. So how to make this laser so narrow, and then doing the clock spectroscopy, and then the quantum state engineering via local controlled and localized dissipation. And then the very recent thing what we are developing here on quantum computing using neutral atoms. And then I will make a summary and then conclude. So this part of talk, actually I'm presenting, so this results from radium after I think at least 5 to 6 years. And then this is actually, I would like to dedicate this part to Professor Das, because this is actually something which make a connection between me and him. When I went for my PhD, so I did not know him, but as soon as I joined, I realized he is one of the top, like within 2 to 3. I mean, there are many people, but there are people who leads the field, who guides the field, and he was one of them. So, so I actually became to know about him from my PhD research group in University of Groningen, that he's one of the kind of leader who shows path to this experimentalists, like where to go, and like this again kind of a navigator. And yeah, so yeah, so like the experiment which I was working on was using radium atom. So radium is basically an alkaline earth atom. This means is that it has 2 electrons in the most outer orbital, and that is one of the reason. And the other reason is its nuclear is not spherical; it's a deformed shape, something like a pear shape. So during my PhD time, this was not tested, but later in UK with Peter Butler's group, they actually tested it in the experiments, that it is really the case for the radium nucleus, that it has a deformation. And these are the things which induces some kind of amplification into the electric dipole moment of electron, if you measure it inside a radium atom. So that was the main motivation for the project. And then for doing this experiment in a very with a very good signal to noise, we realized that we should trap the atoms. And then main trapping transitions would be, I mean, it's an alkaline earth atom. So it has a like a strong transition, singlet S0 to singlet P1. So most of the, so for all the alkali earth atoms, so this is somewhere in the blue. So for us also it was around 483 nanometer. And then we did the spectroscopy of this. So the signal you can see on the left side top, and the bottom one is a tellurium molecular spectroscopy. So this is just to kind of reference this signal. So we had a frequency comb. We calibrated these transitions using that, but You know, this frequency comb is an expensive thing, and also you need a special expertise for operating it. So which might not be available in all places. So that's why we thought, let's do it with both frequency comb and then also with molecular reference. Okay, and then we also did spectroscopy with for the intercombination line. So the story is the following. So if you use the strongest cooling, so you can strongest slowing, I must say it's slowing, you can slow the atoms, but it's the natural line width is not small enough to cool the atom to like, let's say few microkelvin or few tens of microkelvin level. So that's why if you use a intercombination line, then you can reach a much smaller temperature. So that's why normally in all alkali earth atom experiments, you first cool with a strong transition, and then you cool using a narrower transition, which has a line with a few hundreds of kilohertz. So that's what we did here, and we referenced it with the iodine spectroscopy line. So it's again molecular spectroscopy line, and the precision was quite good. So you can see them into so this uncertainty, you can see them into the first bracket. Okay, now I'm switching to another atom, but still this is an alkali earth atom. So these atoms are really beautiful. And especially if you look into this ytterbium atom, this is probably like the most colorful atom I have seen. It's really beautiful, these colors, because most of them are into the visible range. And the main motivation for working, so I worked with this experiment in University of Hamburg. So the main motivation was to look into the Kondo lattice model. So I'm not going into the detail due to the limitation of the time. We could talk about it later, but it has this ground state. It has a couple of clock states, and then you can use these states as two different ground state, and then you could use these two kind of ground state for studying two orbital or SUN magnetism, or Kondo lattice model, or different kinds of topological superfluidity, and also spin orbit coupling. It's also very interesting system to study spin orbit coupling using such alkali earth atom, because when you study the spin orbit coupling using alkali atoms, right, like rubidium or potassium, you get a huge heating due to these Raman transitions. But for the case of ytterbium, you can just connect it using one single optical transition. So that's the clock transition. So that reduces heating by a large amount. So yeah, now how to kind of develop this ultra narrow line with laser for the clock spectroscopy. So normally the this line width of the clock transition is theoretically few millihertz. And now if we have a laser which is let's say megahertz, then we would never be able to kind of probe this line width. So that's the reason why we need to build such lasers which has a very small line width. So basically we take a cavity, and now if you look into just this little formula, you don't have to go into the detail, but the main concept is that this cavity, these are made of some very ultra low expansion materials. It can be glass or it can be 0 and now we have to find out a temperature where the this expansion coefficient has a 0 crossing. I will show the plot in one of the next slides. And now think about if you can find out this 0 crossing, and if you set the temperature of this cavity at that temperature, then for outside change of temperature also the change of length of this cavity would be minimal. And now you can lock this, so you can use this cavity for locking the laser. So there is a technique called Pond River Hall. Basically, you can send the light through this cavity, and you see if you use a Fabry-Paro cavity, then you will see different modes. So Gaussian mode, so that's TM00, and then the higher order modes TM01, and so on, so on. So you can kind of get these modes, basically the TM00, and then do some basically mathematical equations using some electronics mixing and filtering kind of thing, and then you can generate an error signal. And this error signal would be then directly coming from the clock cavity, which is very stable, ultra stable, and that's why the lock would be very stable. So that's why the drift of frequency would be minimal. And also note one thing that this cavity has to be very stable. So that's why we have to kind of shield it with several layers of thermal isolation. And again, all these things are inside vacuum chamber. And what you see in the right side picture, so this whole setup, this is sitting on just on a normal optical table, and on top of that there was a -K table, just to kind of reject as much as possible to this passive isolations. Okay, and now this is the result. So when we make this measurement of this finding this 0 point, or this temperature where this coefficient of thermal expansion has a 0 point. So for that, we basically take measurements into a couple of different temperatures. So basically, we look into a bit node with this light which is going through the cavity to a frequency cone, just to kind of measure, take this measurement with a very good precision. And then we change one temperature, and you see it takes a couple of days actually. It takes a couple of days because the cavity is sitting in a very nicely thermally isolated environment. So that's why whatever change you make, it takes a couple of days. And then when it settles down, so we kind of note that down, and then we repeat this for a couple of data points. And then on the right side plot, you see the temperature versus bit node frequency, and you see there is a 0 correlation. So basically, if we put this temperature of the cavity at this point, then so this cavity length would be least sensitive to any change of outside temperature. And it happened to like 32 degrees centigrade or something for our cavity. And the finesse was in something in the range of a little bit more than 200,000. Yeah. So when we make just one sweep, just a single sweep of this laser, so basically laser line, so then you see that the full width half maxima is just below a hertz. And if we average it over I think it was averaged over 30 seconds or something, and then the full width half maxima is kind of a little bit in the order of 4 to 5 hertz. And this is something then can be used for probing such narrow clock transitions. So just the wavelength for this laser was 578 nanometer. And now we want to look into the clock spectroscopy. So when we want to do clock spectroscopy, we have to load the atoms into optical lattice. So we loaded it into 3D optical lattice. So I just want to give one this slide about optical lattice. So basically, if you take two beams, they have to be definitely identical into polarization. And then if you make some kind of a standing wave, so there would be minima and maxima. And depending on whether it's a red detuned or blue detuned, so atom can be trapped into the minima and maxima. And then if you make one such like a 1D, so if you look into the right side picture, picture A, then there's one set of beams which are making the standing wave, and this is actually making a series of like a 2D planes. So this message I would like to give to all of you, and maybe there are some students. This is an, I think, interesting concept which quite often get mixed up because when you talk about like a 2D system, then we have to use 1D lattice, because you see we are kind of slicing the sample into this series of 2D planes. And now if we add another set of beams in the orthogonal direction, then we slice this each of these 2D system again, and then we get like an array of 1D tubes. And now if we add a third pair of lattice beams, then we get really this like a dot and dot, and this is like a 3D system. Okay. So for our experiment, we loaded the atoms into a 3D optical lattice, and what you see here, this is a clock spectroscopy with a single component Fermi gas of 173 terbium. So just make a spin polarized gas to like just MF equals to +5 state using just optical transitions, and the temperature was like T over T, like T over TF. TF is the Fermi temperature, 0.25. I mean, in real life, this is around 15 microkelvin or something. And full width half maxima was about like a 50 hertz, which is very close to some of the best clocks. And just keep in mind that we did this for doing the many body physics, and that was actually enough so this full width half maxima was enough for that. So I think if I look into the time, I'm just going to skip some of the slides and just
Yeah, you have about 5 minutes.
yeah. So now let me talk a little bit about the non-equilibrium steady states. So the non-equilibrium steady states are quite interesting phenomena, and they can be observed also in classical systems like heat conduction or current flow, or even in supermarket trends. And what about the quantum systems? So these steady states can appear if a system has like a gain and a loss. And when this gain and loss are in a kind of a balancing each other, then one can see it's like a steady state. So note that this is not the equilibrium, right? So it's still in a dynamic, but it's in a steady state. For any kind of quantum system, so the decoherence or environmental dissipation is a big issue. So that's probably the biggest issue. And now there was some theoretical proposal which was showing that if we can provide a dissipative potential or a controlled decoherence mechanism to the system from the very beginning, then after some transient time, this whole dissipation plus the quantum system should be driven to a steady state, which should be then much less prone to any kind of environmental noise. Okay, so that's one of the biggest motivation for us. And then, of course, we can study different kinds of far from equilibrium many-body dynamics. And now we can model this system using such Lindblad formalism. So basically this term with a minus I, this is a non-Hermitian term. This represents, this captures the dissipation or the lossy part. So the system what we had is we had a Bose-Einstein condensate of rubidium, and then we used a scanning electron microscope for making high resolution imaging. But we also use the same electron beam for inducing some controlled loss. So what we can see here. So this work is from my Kaiser-Slaughter's work, and so you can see that we can, in a controlled way, prepare this this lattice sites where we depleted almost all the atoms. So here again, so we did this experiment into a system where we loaded the atoms into 1D optical lattice. This means we are having series of like a 2D system, so like a series of pancakes. And then after creating this pancake, we just removed almost all the atoms from one side. So that's, you see, the central side. And then we reduce the lattice potential so that tunneling can happen. And there are two cases. So in the first case, we you see the red one. So so one thing is that when this dynamics takes place, we always keep the electron beam on, so that always there is a loss, and we can control this. And you see that the red one reaches a steady state after some time. And now if we repeat this experiment without removing the atoms into the central site, then also we see just the states stays there. But it's now in a steady state, because even for the blue one, this dissipative potential is on. So to summarize this part, you can have a look into the first part of this plot. So from 0 to 50, this gamma is the dissipation strength. And so that's something similar to a superfluid behavior. So we are removing atoms, but still they are filling up and they are keeping the level. And then, and these are not equilibrium, but these are the steady state. And if you look into the higher dissipation range, so like more than 200 or something, so both the states are again reaching some steady states, which is different from the first part. And then in between, the interesting thing happens, because we see really two different steady state based on the initial conditions. And this study was quite interesting because now you see that if we could transform this knowledge into the qubits, then we can maybe find steady state into qubits, and then it would be interesting to know, or it would be an interesting platform how large we can make this qubit array, right? Because for increasing the qubit array, as soon as we add more and more qubit, there are more and more noise and decoherence and dissipation into the system. So it could be used as a seed kind of knowledge for exploring the scalability. And Here, actually, I have joined about 8 or 9 months ago, and then we are setting up an experiment where we would like to trap an array of single atoms, so CGM atoms, and then we'd like to explore quantum computing and mostly quantum optimization or error correction in the long-term quantum algorithm developments. And the type of interaction we would like to explore are, of course, with the Rydberg excitation, but also using a spin exchange interaction. Because when you do this spin exchange interaction, you could kind of use the lower hyperfine steps, and then in principle, you could have a longer coherence time. So some of the key advantages of using neutral atoms as qubits are, I mean, they are really identical, very similar to ions. So because these are nature script, I mean, if you have one atom here, and then if you have one even at Mars, they are exactly identical. So compared to other systems like superconducting qubits or silicon, and the miniaturization, so the setup is comparatively smaller. We do not need a large setup. And also in the size of like a large matchbox, we can trap like a 3D arrays of atoms using optical tweezers. So there are some experiments demonstrated already. And we do not also need a large freezers, and the sensitivity to noise is also for the case of atoms much low. They are sensitive, but they are not that sensitive. And when they are not that sensitive, this means it could be possible that the coherence time can be longer there. And there was some highlight about this field also, because using cold atom quantum computing started only few years back. I mean, Mark Chapman was doing it for a long time, but it really get pushed over last few years. And from the time when we could, we knew how to make this defect-free arrays. That was not clear in past, because the loading is basically probabilistic. But now we know how to make the defect-free arrays. And then there are some articles. So there are many articles coming, but one of the article was showing that this neutral atoms is rising as a dark horse qubit candidate. So we'd like to just explore it. Okay, to summarize, I have shown you some precision spectroscopy result in radium 225. The motivation was to search for electric dipole moments, so permanent electric dipole moment for electron, and then shown you some results and how we developed the clock setup, and then this spectroscopy for ytterbium. So sorry for this. So this is not ytterbium 171. This is 173. So that's the typo. And then I showed you some result on how to kind of engineer like a steady states into a quantum system using control dissipation. So I'd like to show you our current team. So this is really great team. So it's really amazing to work with them. So they are all sitting at home now, but still we are progressing. So the first row is the PhD students. So the last one, the first row is doing actually theory in a collaboration with Ravi Shankar. Professor Ravi Shankar in our department, and then the MTech and MSc students, some part-time people who are working, and then the last row is also very motivated BTech students. So we are putting really a lot of effort to make it working as soon as possible, and hopefully in another year or two we could kind of get some new result from us. And besides actually developing hardware, because just having hardware is not enough, right? You have to understand what you want to implement of hardware. So we are also trying to explore on those things. So with that, I'd like to thank you for your attention.
Thank you, Puttaditya, for this wonderful talk. We have a few questions. Let me take it first from Bimalendu. Could you elaborate more about the electron-induced dissipation process?
Yes. So let me go back. Yeah, so actually what happens if I look into this slide, so when the electron beam hits the atom, so there could be a couple of scattering processes, so inelastic and elastic. So in some processes, the atom will get larger energy and then it would kind of fly away from the trap. In some processes, it will get like more than one electrons out of its outer orbital or outer and the next orbitals. But for us, which counts is basically the event where only one electron is knocked out. So that's for the detection. But when we do this dissipation experiment, then all these dissipations takes into place. And this is a one body loss process. not a two-body loss process. Okay, so after preparing this state, when we do the experiment here, so into this central this well where the incoherent loss is there. So I mean, we can tune this dissipation by changing. We don't normally do not change the beam current. That takes long time. But what we do is that we scan the electron beam across this site. So the lattice spacing. So the size of this site would be about 547 nanometer, and the electron beam had a size about like 150 nanometer. So that's why it was possible to only address this site. And of course, to the realistic point, there were some artifacts to the neighboring sites, but we corrected for that. But when we scan it across this, so imagine we keep the time fixed, and then we increase the scan length by factor of 2. So that's how we can change the rate of dissipation. So that's how we kind of implemented this dissipation scheme into our system. Was it clear?
Power for a second. Can we take the next question? If hello, can you hear me?
Yeah.
Yeah. Okay. There is a question from Sandeep Dubey. What does lattice specifically means in an optical lattice? Does it have any similarity with the crystal lattice?
So what was the first thing? What does which mean lattice spacing?
Lattice specifically mean in an optical lattice?
Okay, so
I just wanted to probably clarity on what does this optical lattice means.
Yeah, so in the case of, I mean, I do not have a nice picture here, but I just try to explain. So in the case of like this electron, so this normal materials, you get a lattice of basically this lattice is a potential which is formed due to the ions into this material, and this is actually a periodic structure theoretically, because in materials you get some defects and all other deformations, but in a clear concept type of thing, it's a periodic structure. So what we try to do, or kind of mimic to do, using standing waves using lasers. So you have to take linearly polarized lasers, so, and also the frequency should be defined, otherwise you don't get this very nice clean standing wave. So we make this standing wave, and then you see this minima and maxima, they are periodic. They're perfectly periodic because these are made of light. And now compared to the electronic structure, so I think in the electronic structure, the lattice spacings are like in the angstrom or something like that. But for us, this is a few hundreds of nanometer. So for our case, this was 547 nanometer. So that's why there will be a difference in tunneling time. So for us, this tunneling time is in the order of few milliseconds. We can control it by changing the this lattice height, which is basically by changing the intensity of the light what we are using for producing this lattice. And when the dynamics is taking place in the or in the time scale of like few milliseconds, so it's quite I would not say it's easy because it's still challenging, but it's within the reach of the presently available electronics. So that's why it provides a good kind of a platform for looking into such or mimicking this tunneling or the lattice effects, which are present into the solid state system using our system in a very precisely controlled way.
Okay, there are more messages coming, but since it is a last talk, I take the freedom of asking some more questions.
Okay.
There is a question from Mahesh TP. You mentioned about lambdic regime in optical lattices. What is the minimum temperature you achieved sideband cooling there, after sideband cooling there?
Yeah, so I think you are talking about actually this slide basically. So I should mention, no. So this is my slide. Didn't I show the clock spectroscopy? Oh yeah, right, this one. Yeah, so so first of all, this is an alkali earth atom. So so in the alkali earth atom, as I told you, So we did not use the sideband, it's probably not possible, but we used this narrow transition. So this 500, not 578, but 556, the intercombination transition. So first we cool using the 399 nanometer light. So this is good enough for, we call it a slowing, because you know, in order to trap them, you have to slow them, because normally they are moving with a speed which is much faster than the jet plane. So like, which is more than 300 meters per second. And now if you have a trapping volume using these 6 lasers, it would not be just capture this atom, it will fly away. You need to get in the range of few tens of centimeters, something like that. So that's why we do first like a cooling using the 399 nanometer light, but this is not giving a cold enough temperature. For cold enough temperature, you have to use we use then this narrow line, which has a line width of like a around 200 kilohertz theoretically. And if you look into this Doppler, this formula, then you see that this line width goes into the equation, what you use for calculating the temperature. So that's why we do it using this blue and then green to get a temperature. And for our case, this temperature was about in the order of 10 to 13 microkelvin.
Okay, there is another question from Srinivasa Prasanna. It's a naive question, and maybe I missed your points. Since neutral atom interactions are very weak, would making 2-qubit gate be harder than the trapped ions?
Okay, so yeah, so it's about this slide, I guess. I think I'm not an expert on ions, but I think the interaction in ions takes place via the Coulomb's interaction. So there is a force. For the case of atoms, of course, these interactions are missing. So there are 2 possible ways. So one way is we could kind of bring 2 atoms. So we would be trapping atoms into single atoms into optical tweezer. So that's the first thing. And now, in order to let them interact, so one of the option could be we can bring them together. So we can move the tweezer. And then when they come in the same place, there would be collision taking place. So the cold at the ultra collision. And this collision kind of imprints some phase. So this is one way for generating entanglement, but so note that this is a process which is slow, because you have to kind of move tweezers. And now also it's a bit unknown, like if we scale up the system, then how all these movements will take place. But this is one of the way. But the other way, which is probably more promising, is using Rydberg excitation. So if you kind of excite one of the atom to its Rydberg state, which has a so basically n equals to, so that n is a principal quantum number, so 50 or more, then it's the size of the wave function would be few micrometer. And now imagine there are 2 tweezers which are sitting, let's say 3 or 5 micron apart. Then these 2 atoms could kind of sense each other, and that's how we could engineer interaction between these 2 atoms. Okay.
Okay, I think it's almost 1:30. I think we will take a break now. Let's again thank all the 6 speakers of this morning section. There are questions coming up, but I'm sure you can take it up privately over the email. Because
I mean,
sure
definitely. I mean, anybody
everybody is
has,
quite open to email answering these questions.
Yes.
So I will encourage everybody to please ping the questions directly to the speakers. So thank you again. So before I sign off, let me also thank the organizers giving me this opportunity to chair a section which is organized in honor of my great friend Vanudas. So thank you. Vijay, please take over if you want to announce anything.
Yeah, Simran.
Yeah.
Yeah.
I'm not being able to turn on my video, so I'll just proceed as it.
Oh, okay.
So on behalf of the organizing committee,
have
I
to
would
answer.
take the opportunity.
Yeah, okay. Thank you very much. Yeah. Yeah, so I must, I'd like to thank Professor Pai for, steering this session very nicely and taking care of this questions answer session very nicely. And I would like to also thank all the speakers of the morning sessions. So we'll have a break for 1 hour for lunch, and again we'll assemble exactly at 2:30 just to maintain the time. Okay, see you then.
Thank
Okay.
you. Thank you all.
Hello, Vijaya.
Yeah, I just sent you.
Okay,
WhatsApp
did you get it?
Yeah, I just sent you some messages.
Oh, sent me. Okay,
Yeah.
great. I know that Bhanu has received the list of the awardees, isn't it?
Yeah. But
Okay.
he may not announce the TCG thing. I think that you have instructed Prasanna to do this, right?
Sorry, I
We have to
just a minute.
I am taking care of that.
Yeah, please.
Okay, the sound was not enough. Please.
Yeah. Okay. So the TCG is the acknowledging TCG part will take care.
Sure. That's what the suggestion is. That's what I wrote to you.
Yeah. No, I'm cross checking with you again.
Yeah, no problem. So that is one aspect. The other is the list of the felicitation speaker in a sequence I have sent now.
Yeah.
So just have a look.
You are supposed to record that on cloud, okay? It may be I think.
I would prefer that, yes, if possible.
By the way, this conversation is still being beamed on YouTube live, right? No?
Okay.
Oh, so what do? We just switch it off or?
Leave it.
Okay.
I think let's talk over the phone.
Okay.
Okay, I can do that. Yes. Okay, I'll do that. Thanks.
Hi, Sunaga-san. Nice to see you. Oh,
hello.
Yeah. So congratulations for getting new job. I didn't know that
Okay,
you joined in Kyoto.
thank you. Yes, I have a good luck. Yeah, very lucky.
I see. When did you join?
Well, from this April.
Oh, recently.
Yes,
Okay.
recently, yes. So just after the graduation.
Okay.
Yes.
So you are still collaborating with this Dirac people?
Yes, actually, yes.
Okay.
Yeah, so by email or this discussion via Zoom. So I attended the annual meeting of Dirac family. So yes, good communication. Yes.
Great.
Yes.
Okay, see you soon then.
Okay, see you.
Yes. Oh, I'm sorry. Oh, yeah, I just forgot. I thought that I had
So should I begin?
Yes.
I mean, I'll just make a couple of quick announcements and then introduce the speaker if that's fine with Professor Sahu and Professor Mukherjee.
Yeah, fine. Prasanna, you do it.
Okay, sure. So I'll begin then. So hello everyone. And like I said, before we begin with the contributing talks, I'll make a couple of very quick announcements. After the conclusion of the last scientific session, which is roughly about 2 hours from now, so it's at 4:15 p.m. Indian Standard Time, the poster awards will be announced. The awards are sponsored by TCG Crest Kolkata, and in fact, Professor Das is the director designate for the Quantum Sciences and Technology Department of the institute called Secure. That's the first announcement. The second announcement is that the felicitation program will commence at about 4:30 p.m. Indian time, shortly after the announcement of the poster awards. So now that I made both the announcements, we'll begin with the contributing talks. I'll introduce the first speaker, Dr. Ayaki Sunaga from Kyoto University. So Sunaga-kun, please start. Thank you.
Okay, thank you. Do you see my slides?
No, not yet.
No,
not yet.
really. Well, okay, I understand. I understand. So this.
I think you need to share. Yeah, now I think.
Yes.
Yeah, so it's a 15-minute talk, so inclusive of questions. So
yes.
Yeah. Okay. Thank you.
Thank you. Thank you for your introduction. And I'm Ayaki Sunaga, and I will talk about relativistic many body calculations on molecules, including effective QED potentials. It is a collaborative work with Tron Sao. Yes, in the relativistic many body calculations, to get good accuracy, there are 3 dimensions: basis set, correlation, and Hamiltonian. About correlation, the correlation methods, for example, couple cluster, have been dramatically developed by Professor Banu Pratap Das and Professor Devasith Mukherjee, and so on. Now, the correlation axis becomes good, so it is the stage to get the good accuracy, better accuracy in the Hamiltonian. It means including QED effect. However, real QED approach are too expensive for molecules, so our approach is a practical effective QED potentials in the 4-component program. Then, what is quantum electrodynamics QED? The basic idea of QED is a vacuum fluctuation. Energy in a point in space can be temporarily changed because the time-energy uncertainty relation. This allows the creation of virtual particle-antiparticle pairs, and in my case, electron-positron pairs. It is the vacuum polarization. A nucleus is surrounded by virtual electron-positron clouds. And the nuclear charge is screened by vacuum polarization, but s orbitals, which are with contributions close to the nucleus, there's larger nuclear charge. Another kind of QED effect is self-energy, which mainly contributes to Ram shift. In the framework of Schrödinger equation, S half, P half, P3 half are degenerated, but in the framework of Dirac equation, S half, P half, P3 and P3 half are splitted, and because of the spin-orbit splitting. And in the framework of QED, S half and P half are splitted, and it is called Ram shift. Then, how should we include the QED effect in the relativistic many body calculations? Our approach is effective QED potential for including QED effect. We add effective QED potentials, which is a one electron operator in SCF procedure like this. There are 2 kinds of effective QED potentials: vacuum polarization and self-energy. For the vacuum polarization, we use Ewing potential, and there is an analytical expression for this. we implemented two self-energy potentials, and the first one is a Picot-Chow model potential. It is the Gaussian model potential with two parameters for base set calculations. And the second one is Flambourn-Ginzer's effective potential, which is more elaborated than the model potential. There are three terms for this potential, and it was derived by second-order radiative corrections. The formulation of effective 3D potentials looks complicated, so how should we implement it? Our approach is the numerical integration. We use the Linus numerical grid for the radial part, and we use the Lebedev angular quadrature for the angular part. In the practical implementation, we ported effective 3D potentials from grasp code. And for the numerical integration, we use existing DFT routine. And for the radial integration, we can cut off the radial part because of the locality of effective 3D potential. The main advantage of this approach is effective 3D potentials are available for all electronic structure methods in Dirac code, which means we can calculate all of the molecular properties in Dirac code with effective 3D potentials. Next, I will show the results. So first, I compare between relativistic effects and 3D effects. In a previous work, it is known that the RAM shift is about 1 or 2% of the kinetic relativistic effect for both alkali and coinage metals. But the target of reference 1 is only ionization potential, so we calculate other properties. It is a result of the bond length and root mean square radius of gold system. It is a non-relativistic one and relativistic without QED effect and with QED effect, and the relativistic effect and the QED effect, it is a absolute difference, and it is the percentage of between QED effect and relativistic effect, as shown this. From this table, the percentage between QED and relativistic effects of root mean square and the bond length are about 1%. And the magnitude of the order of the magnitude of QED effect is ionization potential, root mean square, and bond length. This order is corresponding to that for bond length, the valence region mainly contributes, but the ionization potential, core region can contribute because 6s orbital is distributed to the core region too. Next, we show the comparison between calculation with QED and experiment. It is a result of the bond length of AUCN, and we use X2C molecular mean field Hamiltonian and CSD parenthesis method. And the main improvement compared with previous work is we include Ghon's term and QED effective QED potentials. And this table shows the result. And from this, our calculation, it is our calculation, and including triple correction and quadruple correction, and including the QED effect. And as a result, our value agree with experimental value very well, and the agreement is better than previous works. From this, QED effects improve the agreement with experiment. Next, we show the result of molecular core properties. The first example is parity violation, which is defined by this operator. Our target is a simplet chiral molecule like this, and from this table, QED effect is about 1 or 2%, and the absolute value of QED effect is proportional to Z to 7.6, and which is clearly larger than the QED effect of ramp shift, which is proportional to Z2 force. From this, QED effect is non-negligible for core properties of heavy molecules. The next example is electric field gradient, EFG, which is defined by like this. From this table, QED effect is also about 1%, and about EFG, there is an experimental value. So comparison with experiment at the CSD level is desired. Next, we show the test calculation of effective electric field at the CI level. And this is relativistic calculation without QED and absolute difference and percentage. From this, QED effect, the QED effect itself is increased as Z becomes large, but the percentage of QED effect is about the percentage of QED effect, the trend is changed. The reason for this is effective electric field is increases as Z becomes large, and it is faster than QED effect. And the QED effects in effective electric field are about 1 or 2%. Next, we mention about the QED effect to decrease effective electric field. To understand this trend, we calculate the radius and ionization potential of AU atom. From this calculation, the QED effect for radius is that radius is expanded by QED effect, so electron density at the nucleus is decreased. It is that the electric field that electron feels is decreased. It is the reason of the decrease of E effective. And finally, I show the comparison with QED and other effects. It is a previous calculation of thorium oxide and YBOH. And from this comparison, QED effects are as important as other high-order corrections for the accurate calculation of E effective. It is a conclusion. We implement of effective QED potentials in Dirac code, and it is available for all electron structure methods available in Dirac code, and we have a plan to release our effective QED code in Dirac 20. And we show the application of effective QED potentials, and the agreement with experiment is good, and for molecular core properties, QED effect is important. Finally, I would like to thank Professor Banu Pratap Das, and it is photo in 2015, and when I was a fourth year bachelor student, and we had a lot of discussion, and we published a lot of paper. So thank you very much, and happy birthday, Professor Das. That's all.
Okay, thanks a lot, Sunaga-kun, for your excellent talk. We still have 3 minutes. I don't see any questions in the chat box in Zoom or on YouTube. So if there are any questions, since we have 3 more minutes left, I request you to post it on the chat box. Okay, if not, then I have just one question for you, Sunaga-kun. So
yes,
in your AUCN calculations, the virtual cutoff was 50 AU, right?
Cutoff, which part? Well, what do you mean virtual cutoff?
The cutoff of virtuals whose energies are more than 50 AU. Is that what it means when you say 50 AU for AE3Z?
Yes. For the more than 50 atomic unit, we don't include the virtual orbitals more higher than 50 atomic unit.
Okay, so that's a reasonable approximation, is it? So it doesn't change so much, is it, in these 50 AU?
Well, we don't run so much calculations. For example, we don't run 100 to 200, 300, and so on. But we confirm that for the 3Z base set, we in the 50 atomic unit, we can include G orbitals. So okay. It should be fine. And for the AU4Z, within the 80 atomic unit, we include I orbitals. So it is fine. Yes, it is the reason of the 50 and 80.
Oh, okay, great. Okay, thanks
Yes.
a lot. So if there are no other questions.
There is a question in YouTube.
Okay.
Let me read it for you.
Okay.
So it is by Martin. Hope this question is not too long, but I would like to know how one can construct these effective potentials.
Construct, well, yes. Well, it is derived from the scattering between nucleus and electrons. So the scattering between electron and nucleus, and we can define S matrix and S matrix in the within the perturbated approach. We can include the first term is only Coulomb part, 1 by R, and the second order is this magnetic part and high frequency part, and the high frequency part, the analytical formula. The simple answer is scattering between electron and nucleus. So it is not the bound state.
Okay, so I hope that answers the question. So I'll thank Dr. Sunaga for his nice talk. Thank you for coming.
Thank you very much.
Thank you. The next speaker is Mr. Akitada Sakurai. He's going to talk on chimera-like discrete time crystals in a quantum spin network. So Sakurai-kun, are you?
Oh, sorry,
okay.
Thank you.
Yes, thank you.
So I want to share my screen, but Sunaga-san is sharing his screen.
Yes,
Can you?
Yeah. Fine. Looks fine.
Yes.
Yeah, thank you.
This is fine.
This one. Sure.
Yes. Yeah, we can see the screen. So you have 15 minutes, including questions, Sakurai-kun.
Okay.
Okay, thank you.
Okay, thank you. First, I would like to thank the organizers for allowing me to talk at the FQST 2020 in honor of Professor Das on his 65th birthday. So before my talk, I would like to briefly express my gratitude and appreciation to Professor Das. So he was my supervisor during my master's program from April 2017 to March 2019. Under his supervision, I did a numerical calculation of the xenon ETM using the relativistic coupled class theory. And for this, the first time we met at the information session for the graduate student at Tokyo Tech, and I visited his lab, and he was very kind, and he explained to me how his research area is exciting and important in physics. I will never forget the day. So, and before I joined his lab, I didn't know the theoretical physics, including quantum mechanics, because my bachelor's degree is mechanical engineering, but he taught me from the basics of the quantum mechanics. And this photo is from when he was teaching me the relativistic quantum theory. So my 2 years with him have been delightful and wonderful. Here I'm very grateful for all that he done for me. Okay, now let me talk about my recent work. So the title is a chimera-like discrete time crystal in quantum spin network. So we found a new phase of matter in periodically driven system. In this state, two different phases of matter coexist in the same space. So before going to model, I would like to start with symmetry and symmetry breaking. So symmetry breaking is a universal and general concept in many physics, ranging from the condensed matter to particle physics. For example, time reversal and parity violation at the high energy physics give rise to the atomic and molecular EDM. And symmetry breaking also plays an essential role in understanding the phase transition. For instance, in the liquid, phase, a state has a continuous translational symmetry. And here, the state symmetry match with that of the system. However, in the solid state or crystal phase, a state breaks the continuous symmetry spontaneously. And now, like a crystal, we can also consider the continuous time translational symmetry and giving rise to crystal order along the temporal axis, and which is proposed by Wilczek in 2012. So the new phase of matter is called time crystal. And similar to crystal, if the state breaks the time continuous symmetry, there should be some physical quantity spontaneously oscillating. But soon it is proved that the exotic phase cannot exist in the equilibrium system because the state is in equilibrium, which means that it should be time independent. But instead, time crystal can realize in non-equilibrium systems. For example, time crystal can realize in Floquet system. In this system, Hamiltonian is time periodic, and when state spontaneously breaks this discrete time translational symmetry, discrete time crystal will be realized. And now, there is a physical quantities that exhibit the period longer than that of Hamiltonian. And this subharmonic oscillation has a rigidity to the perturbation effect. And this is the periodic. Periodic Hamiltonian is an example of the discrete time crystal. And here, the first term is a global spin rotation on the XZ axis. Now, what is the order parameter of the discrete time crystal? In the crystal, atoms and molecules periodically arranged like this. And alpha, here alpha is a relative interval. And there is some observable which has a long-range intercorrelation like this. And similarly, in the discrete time crystal, there is a physical quantity that dynamics at time periodic, which is longer than the period that of Hamiltonian. And in this system, local magnetization dynamics shows such a phenomenon like this. As you can see, now the magnetization period is 2 times longer than that of Hamiltonian. And discrete time crystals have been realized in many experiments. For example, it was realized in trapped ions and nitrogen vacancy spin parity in diamond at room temperature. Now, let's move to our recent work. So, before, I would like to briefly explain to you the original chimera. So, chimera comes from the Greek mythology. It is a beast like this. So, it has a lion's head and goat head, and its tail is a snake. And in the recent years, the word chimera has been used to mean that consisting of several different parts. And similarly, in the classical nonlinear system, there are states in which synchronous and asynchronous behavior coexist in the same space. It is called a chimera state. But because the quantum system is a linear system, it is unclear whether chimera state can be emerged in the quantum system. In our work, we consider a chimera-like state in quantum system in which 2 different phases of matter coexist in the same space. Specifically, we consider a spin network in which a spatial and temporal order coexist, like this. And we refer to a new phase of matter as a chimera DTC. In this state, ferromagnetic phase and discrete time crystal phase coexist in the same network. And to realize such a chimera DTC, first we employ the spin network governed by the Ising model, like this. And in this system, there is a special long-range correlation. For example, a state free polarized along the z-axis has a correlation. Now, to generalize the correlation along the temporal axis in subregions, for example here, one here, we need to break the discrete time translational symmetry. And to break this symmetry, we apply the periodic driving to subregions of the network like this, and consequently, discrete time translation symmetry is broken in these subregions. And then a subharmonic oscillation will emerge. Now, its Hamiltonian is represented by like this. And then the first part represents the local driving for subregions. And the second Hamiltonian is Ising Hamiltonian for the disordered spin network. And here I'm showing the numerical result of cumulative DTC on one-dimensional spin chain with 8 sites. And the left panel shows dynamics of local magnetizations. Here, vertical axis is a period and the horizontal axis is site. And the left panel shows it's a Fourier spectrum, and horizontal axis is the frequency, and vertical axis is the amplitude. And as you can see, now the dynamics of magnetization clearly show the two different behavior. In this region, dynamics is periodic with a 2T period. And in this, and correspondingly, there is a peak around 0.5 in the spectrum, which means that the phase of matter in this region is a DTC phase. And on the contrary, local magnetization in this region is a constant over time, and its spectrum has a peak around 0. But it has a spatial correlation. So it means that the phase of matter of this region is a ferromagnetic. And from this result, we see that the two different phases of matter are coexisting in the same space as we expected. So next, I'm showing the cumulative TC with a small perturbation on the strong interacting chain, spin chain. So here, that function is a similar function to the 2 times correlation function or local magnetization. And it is used to see the DTC dynamics stability at longer times. And as you can see, despite stronger interaction, there is a strong interaction over the network, the DTC on the cumulative DTC is stable. And it indicates that the many-body interaction plays a role in the error correction for the DTC's subharmonic oscillation. And furthermore, the result means that the DTC on the cumulative DTC are in the pre-thermal region. And the time scale of DTC diverges exponentially in the system size. So this is a summary of my talk. So in this talk, I show you the new phase of matter called the cumulative DTC, in which a DTC phase and the ferromagnetic phase coexist in the same space. And in the cumulative state, even there is a small perturbation, two phases stably coexist. And thus we are thinking cumulative DTC will be used in quantum memory. And finally, most work is done together with Professor Kai in the National Institute of Informatics, Tokyo, Japan, and Victor and Bill, they are researcher in NTT Basic Research Laboratories. And she is my current supervisor, and she and Bill give me a lot of advice in understanding the quantum nature of cumulative DTC. And Victor is an expert on the quantum chimera and the quantum probability theory. And I received a lot of helping from him when we analyze the cumulative DTC system. So here I would like to express my great gratitude for their contributions. Thank you for your attention.
Thank you, Sakurai-kun, for your very nice talk. We have a couple of minutes, so there are 2 questions from Abra. If it's okay, I'll ask only the first question in the interest of time. So the question reads, is it possible to simulate discrete time crystals on a quantum simulator? If so, what platform is favorable, a photonic qubit or the one IBM uses?
What do you mean? Sorry, I don't understand. So
yeah, sure. I'll just copy paste the question on the chat window.
Yeah, please.
Yeah.
You mean we can use a discrete time crystal to simulate some quantum?
Yeah, I think that's the question. The question says, is it possible to simulate discrete time crystals on a quantum simulator?
On quantum simulator, I think it's possible because, for example, ion and trap ions or nitrogen vacancy in purity in diamond, or maybe we can also simulate the discrete time crystal, Chimera DTC by using the superconductive qubits. Yes, it's possible, I guess.
I see. Okay. There's one more question, but maybe they can email it to you because of the time constraint that we have. So thanks a lot, Sakurai-kun, again for coming and giving this wonderful talk.
Thank you.
Thank you. Our next speaker is Ms. Nanako Shitara, and her title is Many-Body Physics for Fundamental Physics, using the coupled cluster method for electron-electric dipole moment searches. So Nanako-san.
I needed to stop sharing. So wait a moment.
Yeah, yeah.
Oh, how can I stop sharing?
I think
you stop sharing. Yeah, yeah.
Okay, thank you.
Okay. Can you see my screen?
Yes.
Cool. I'm just gonna go full screen. Can you still see my screen?
Yes.
Yes. Good. Okay, great. Okay, cool. Okay, then I'll get started then, I guess. First of all, I'd like to thank the organizers for this, for inviting me to this wonderful workshop. I guess I'll just get started on it because I don't have too much time. But as has been introduced, this is the title of my talk. I made it a little bit long, but I hope this gets the message across. But this work is basically the work that I had done for my master's thesis under the supervision of Professor Vanu Das, whose 65th birthday we're celebrating on this occasion. And this was also this was undertaken at the Tokyo Institute of Technology. My current affiliation is at the University of Colorado Boulder as of about a month ago, continuing on and doing a PhD in physics there. So so that's just a quick introduction to myself. Okay, cool. At the risk of boring the audience, I'm just gonna go through and briefly introduce the concept of permanent electric dipole moments of fundamental particles. I know there's been lots of talks so far over the few days about electrons and neutron EDMs, so you might have heard this many times already, but I'll try to keep it short. So basically, an electric dipole moment, first of all, if we just think of the basic definition of it, is this what you learn in undergraduate. This equation that I put up here, the D equals QR, it's some sort of pair of charges separated by a distance r that creates like an electric dipole moment. And that's the simplest case. Generally, we think of an electric dipole moment of a charge distribution. So we have some sort of distribution of charges, maybe they're point charges or something. And you can think of the electric dipole moment of that distribution of charges as this expression right here, this integral. This integral right here. But I'm going to be talking about an electric dipole moment of an electron, which sounds quite strange because an electron, you typically think of an electron as a point charge, sort of point particle, and you might be confused as to how sort of a single point charge can have an intrinsic electric dipole moment. And the very basic sort of intuition for this is that in field theory, sort of field theoretic models, like an electron is actually not the end of it. There are what we call virtual particles, which are the mediators for the forces that elementary particles undergo. And it's these virtual particles that sort of these virtual particles kind of surround an electron, for example. And it's this distribution of the virtual particles around the electron that gives it its effective sort of electric dipole moment, since you can think of this cloud of virtual particles as a charge distribution. Now, and that gives the electron an intrinsic EDM, or so we think. The thing is, it hasn't been measured yet, so we don't actually know if it exists or not. But yeah, and that's sort of natural considering that, yeah, if the electric dipole moment, EDM, is caused by this virtual charge cloud, you can expect it to be quite small in a sort of magnitude. Okay, and just another thing that's quite important for understanding the significance of electron EDMs is it turns out that just from like theory considerations, if electrons or any other fundamental particles have an intrinsic EDM, it implies parity and also additionally time reversal violation if we are considering the CPT theorem. So this just an illustration of this is given, and I think you might have seen it before over the past few days, but anyway, the basic idea is that if the electron has an EDM, it should be parallel or anti-parallel to the spin, and so if we apply the time reversal transformation or the parity inversion transformations, it only inverts one of the two vectorial quantities, which means that we're ending up with something that looks different from the initial state, which means symmetry is violated. So, and it's this it's the T violation part that's quite significant for it has significant
I think
What
the
has happened?
speaker.
Yeah. I think she lost her internet connection probably.
Yes.
Oh, really? Okay.
She
Oh,
will.
I see. I rebooted my machine thinking that I have problem.
Yeah, I did the same, and then I realized that it's probably, yeah. So maybe we can wait for a minute or so for the speaker to reconnect.
Yeah, and also allow her extra time.
Yes, certainly. Oh yeah, she's back.
Oh,
Okay.
good.
Yeah, Nanku, you have to unmute yourself.
Yeah, I've unmuted her now.
Great.
Am I muted?
No, now you're unmuted. So yeah.
Oh,
Yes,
good.
now I can.
Okay, cool. Okay, sorry about that.
Okay. Yeah. Please carry on.
I'll just continue on with it. As I was saying, so there are lots of models of particle physics, and obviously the one that's the most famous and the most successful is the standard model, but for many reasons we all believe that it's incomplete and that it kind of explains some of the observations we that have been sort of some of the observations that have been reported. So lots of people have been coming up with new sort of beyond the standard model theories, and it's kind of hard to test all of these new beyond the standard model theories, like which ones seems more plausible or not. But one way we can, using sort of experimental efforts, is to by measuring the electron EDM. So if we get a sense of the magnitude of the electron EDM that can constrain some of these beyond the standard model theories, and we can kind of get an indication into, okay, which theories predict the right range of electron EDM magnitudes. So that's sort of a really big motivator for electron EDM searches. And there are lots of efforts sort of currently ongoing that are trying to measure the electron EDM magnitude. And it's all very competitive, I would say. So it's sort of very exciting stuff. Yeah, but today I'm not going to be talking about all the experiments that are going on, although those are certainly very exciting. I'm going to be talking about the theoretical aspect of electron EDM searches, and in particular the theoretical aspect of electron EDM searches using atomic candidates. So just to explain very briefly the role of theory in this electron EDM search, I'm just going to talk about just a little bit of equations, I guess. So what happens in an electron EDM search experiment is that we have some sort of candidate, an atom or a molecule, typically. And I'm going to be talking about an atom, so I'll just talk about atoms from now on. But in principle, it can be done with using molecules as well. So what we do is we take a candidate atom and apply an electric field, an external electric field to the atom. And that gives us sort of the atomic EDM of the atom. So you apply a field and then it induces sort of this atomic EDM, and that can be measured as an energy shift of the atom. And the energy shift is related to the atomic EDM by the first equation right here. So we set the external electric field magnitude in experiment, and we measure the shift in energy, and we can obtain this atomic EDM from that. But that's not what we want. We actually want the electron EDM instead of an atomic EDM. So what we have to do further from here is that after you're able to determine the atomic EDM from experiment, you need to sort of decompose that into the electron EDM component, D right here in the second equation, and then this factor R right here. This factor R is called the enhancement factor. And this is not something you can obtain through experiments. You actually have to calculate this theoretically. And furthermore, this value differs for different species of atoms. So it becomes very important to be able to figure out this enhancement factor to a high degree of accuracy in order to get any sort of useful information from experimental results. So this is one of those very nice areas in physics where both the experiment and theory sort of are crucial elements for obtaining a useful outcome. And this evaluation of R is what I will be talking about in this work, in this sort of talk. So, okay, and I'm going to be focusing on a specific candidate, the francium atom. So, and I'll just sort of explain a little bit why that's chosen a little bit later as well. But just some sort of mathematical, I guess, sort of, or physics, a little bit of physics there, but not too much. The basic idea of what we do theoretically is that remarkably, we don't have to use any sort of particle physics. Well, I mean, you do, but like not beyond a certain point, you don't need to use any particle physics. You sort of assume that there is a non-zero electron EDM that exists, and then from there you work sort of in the realm of sort of ordinary quantum mechanics, or relativistic quantum mechanics actually, but sort of not really field theory so much. Anyway, so we start off with like a Dirac-Coulomb Hamiltonian, a typical sort of very standard Hamiltonian, and we suppose then that the electron EDM, there's a non-zero value of the electron EDM. Then we can see that sort of adds this perturbative term to the Hamiltonian. And you can see that this perturbative term, which is highlighted in red, is sort of the interaction between the electron EDM and sort of the internal electric field of the atom. Now this, we know that the electron EDM must be small because we haven't seen it yet. So we can treat it as a perturbation and apply standard perturbation theory to this. And this actually gets us an expression for the atomic EDM, which is given by this equation in the purple box right here. And this is what we sort of use. Okay, this can be simplified further later on, sort of, as you can see on this slide, this is basically the simplified version of it doesn't look simplified, but it is, of the atomic EDM expression. And it's simplified because you're looking at the operators you're evaluating. Yeah, the operators you're evaluating are a little bit simpler, and that's just through some algebra, but nothing too exciting. Anyway, yeah, so we get an expression for the atomic EDM, and what we want is the enhancement factor, right? And the enhancement factor by definition is just the atomic EDM divided by the electron EDM magnitude. And we can see that the expression for the expression for the electron EDM is within this expression for the atomic EDM, because we took the perturbed form of the Hamiltonian, and then we only took up until sort of first order and the electron EDM. So it sort of cancels out nicely to get an expression for R, which we then evaluate sort of numerically. But
just a quick reminder, you have about a couple of minutes left. Yeah,
a couple of minutes. Okay, I'll go very quickly from here. Okay, so it's not too exciting, but I mean, it is quite nice. Okay, but for this, we need to evaluate these wave functions, so the non-perturbed and the first order perturbed wave functions, which are given by this expression, and that is done through some numerical methods. And the first step for that is called the Dirac-Fock method, which is basically constructing a many-body electronic wave function from sort of single electron wave functions. And this basically gives you a starting point, but it disregards electron correlation effects, which can be quite important depending on what system you're looking at. So what we need to do is look at a relativistic couple cluster method, which is a post sort of Dirac-Fock method, and basically uses the very simple statement in quantum mechanics that any state is a linear combination of basis states. So we take the Dirac-Fock state as sort of one element of a set of basis states, and then we construct a complete set of basis states starting from the Dirac-Fock state, and then just listing down the excitations of this Dirac-Fock state. Sort of maybe you have one electron excited into a higher sort of orbital, and that can be considered another element of the set of basis states, et cetera, et cetera. So we can construct our general wave function like this. But this is just the configuration interaction picture. So to bring it to couple cluster, we need to group it in terms of cluster operations. So that means we need to differentiate between exciting one electron, exciting one electron into an excited state, and so you need to differentiate between a 2-particle 2-hole excitation and 2 1-particle 1-hole excitations, because they are in principle different processes. So, and that gives us a nice expression for the couple cluster wave function given by sort of this in the purple box at the bottom. And this is what we use to solve for the amplitudes that are necessary to construct this numerical wave function. And yeah, so that's just done by solving the Dirac equations, the unperturbed and the first order perturbed respectively, to obtain the amplitudes. And the codes to do this were authored by Professor Sahu. So I thank him for his contributions. Without it, I wouldn't have been able to get any results, which are listed right here. So these just list the enhancement factor values using the Dirac-Fock result, and also using the couple cluster singles and doubles method. And we can see that it's something close to 800 in total. And these calculations were performed. They're very sort of high cost calculations, and they were performed on the Tsubame supercomputer at Tokyo Tech. So yeah, I thank GSIC for that as well. Okay, and then this is, I'll just skip that. Actually, I don't think I have time. So anyway, I think this is about it. Yeah, this is just a summary. I don't need to go through it. And I just wanted to share like the photo from this March, I guess, March of 2020. This was my graduation, and also Mr. Sanada's graduation as well. And this was the group photo for the DAS group at Tokyo Tech. Anyway, okay, yeah, thank you. Sorry, took a bit of time.
No, not a problem at all. Okay, thanks a lot for your nice talk. So we are running late already, but I'll just quickly ask one question from YouTube. The
Yes.
question asks, does CPT symmetry also hold for entangled electrons? So I'm not sure how relevant that is here, but yeah, that's.
I mean, it's sort of CPT theorem is supposed to be, well, it's thought to be a universal. Well, you know, I guess we can't say for sure, but like, you know, we're thinking it's a universal thing, holds for anything, right? Then it holds for the entirety of the universe.
Okay.
And that's the whole point, right? So.
Okay, great. Thank you for your nice talk then.
Yeah, thank you.
Thank you for joining us. Yeah, the next speaker is Mr. Aoi Hayashi. He's going to talk on physics of three-body constrained dipolar bosons in double-well optical lattice.
Okay, now I'm sharing my screen. Just a moment.
Yes. Okay.
Can you see my screen?
Yes, we can see your screen now. So you have about 15 minutes, including questions.
Okay.
Okay, thank you.
Thank you for kind the introduction, and I'm so nervous because this is first time to make presentation in open conference. So thank you very much for this opportunity. I'm very honored. Before I start my presentation, I would like to say happy birthday, Professor Das, and thank you very much for everything you've done for me. You always have supported and encouraged me, so thanks to you, I was able to enjoy study and discussions, and I can continue to enjoy them. I was able to learn not only academic things, but also things regarding personality. You gave many kind words and motivated me. I'm very happy to be your student, even though only 1 year. I'm definitely sure the term will be a large part of my life. Again, happy birthday and thank you very much. Lastly, I would like to thank Professor Mishra, who is an organizer of this conference, and Dr. Mondo, who is his student, and Mr. Sakurai, who is a contributing speaker. Thanks to their kind supports, I was able to study and I can make this presentation. Now, let me begin my presentation. In this presentation, I would like to share our ideas on what I'm going to study for my bachelor's thesis. Okay. Over the past few decades, quantum phase transitions in optical lattices have become more attractive as quantum technology has improved. Quantum phase transition QPT are phase transitions driven by quantum fluctuations arising from Heisenberg's uncertainty principle at zero temperature. Optical lattices are arrays of potentials induced by interfering laser beams, and they have use of controlling system parameters. In 2002, QPTs in optical lattices was observed. It is superfluid mode-insulator transition. The Hamiltonian for the QPT is this, where T and U corresponds to kinetic energy and on-site interaction energy, respectively. And A is an annihilation operator for bosons, and N is a number density operator. In the first summation, the indices run over nearest neighbor sites. By varying laser intensities, we can change the ratio U over T and realize the transition. The reason can be given by qualitative discussion. If T is dominant compared with U, bosons can move easily into optical lattice. On the other hand, if U is dominant, high potential will prevent bosons from free moving. As I said, it is easy to manipulate optical lattices by changing laser configurations. Hence, we can consider double-well optical lattice and three-body constraint. We consider one-dimensional double-wave optical lattice and asymmetry body constraint bosons. Their feasibilities are referred in reference 3, 4, and 5. Three-body constraint means to restrict the number of bosons on a single site to less than 3. In other words, the cube of annihilation operators on site is 0. A theoretical prediction to realize the condition is given in reference 4 using a three-body loss process resulting from the elastic scattering of atoms. Double-wave optical lattice has staggered hopping amplitudes as the figure is shown. Firstly, we consider a limiting case where U is infinite. In this limit, only a single boson can be on a site. In other words, the square of a dagger is 0. If the optical lattice is homogeneous and all the sites are filled, then the system indicates motor insulator phase because of the cost of infinite on-site energy. However, for the case that n is less than L, it indicates superfluid phase. Furthermore, we can find longer coherence lengths in the phase. In double-wave optical lattice, however, a specific phase will arise. For n equal to L, the system is similarly motor insulator phase. The specific phase arises at half filling. A boson moves only in an isolated unit, including two sites with T1 hopping amplitude. The boson cannot straddle over higher wells. Hence, the coherence length becomes shorter than in a homogeneous optical lattice, and a gapped phase arises. The phase diagram is shown in reference 3. The phase is called bond order phase. For the case that U is finite and attractive, we can also find a characteristic phase which is similar to previous one. The existence of attractive on-site energy results in forming pairs of bosons. Thus, the pairs move around and it is pair superfluid phase. Similarly, in double-wave optical lattice, pair bond order phase can arise. However, in general, bosons interact with each other at long range. For example, Coulomb interaction, dipole-dipole interaction, and so on. Then we consider the case that long-range interactions decay rapidly. In other words, we consider only nearest neighbor interactions. According to reference 7, in homogeneous optical lattice, the existence of such interactions can result in a super solid phase and a charge density wave phase. For example, at half filling for repulsive nearest neighbor interactions, CDW phase can arise. In the phase, bosons are placed on alternate sites like 1, 0, 1, 0, 1, 0, and so on. If a boson is added to the phase, boson may move freely with remaining the CDW order. It is super solid phase. In the phase, diagonal long-range order and off-diagonal long-range order coexist. Okay. We can infer the dynamics in double-wave optical lattice from previous examples. Firstly, we assume V is repulsive and U is infinite. For small values of V, we can find the bond order phase at half filling. However, for bigger values of V, the energy cost of bond order phase increases due to this state. Hence, the states are suppressed then we can find the CDW phase. Sorry. Okay. For attractive nearest neighbor interactions, different transitions arise. For small values of V, similarly, bond order phase arises. Slightly increasing V, the system would go into superfluid phase because bosons can obtain energy gains from inter-unit hopping with T2 compared with intra-unit hopping with T1. For much larger V, bosons will be assembled in one place. Then full states and empty states are completely separated. This is phase separation. Secondary, as we discussed in the previous section, we can expect to exist a pair bond order to pair CDW transition, and pair bond order to pair superfluid to pair phase separation to transitions, with increasing the absolute value of V. However, there exists more interest which cannot be explained by intuitive discussion. For example, how we'll change the phase diagram in detail. How will be the phase when we add or remove a boson or a pair of bosons to CDW phases. And what are the types of phase transitions between phases? Therefore, we are going to investigate our model by using numerical computing methods to reveal new phase physics. Summary, let me summarize my talk. In the double-well optical lattice, we can obtain the bond order phase. For three-body constraint bosons, the dynamics of pairs of them arises. Assuming nearest neighbor interactions in a double-well optical lattice, it may be possible to find the transitions from phase driven by the nature of double-well lattice to phases by such interactions. As a result, by simple assumptions, we can find interesting various phases in optical lattices, and the assumptions can be realized and be investigated experimentally due to the controllability of optical lattices. Thank you very much for your attention. That's all.
Okay, thanks a lot for your very nice talk. Any questions from the audience? There are no questions from YouTube, so. Okay, there's one question from Sakurai-kun. Do such systems exist only in nearest neighbor interaction?
Do such systems exist only in such system? Sorry. What system?
Can you go to your model? I think you assume that there's only nearest neighbor interaction, I guess. So what will happen if there is a long-range interaction? For example, that's one, page 9. Slide 9, can you go 9? Okay. If there is a long-range interaction, so what will happen? Is it still you get such a interesting phase, or it will be different?
Sorry, can you explain again?
If there is some long-range interaction, I think this system is only nearest neighbor interaction. So what will happen if there is?
No. Here we assume only on-site energy, so without nearest neighbor interaction.
So what will happen if there is a long-range interaction?
Or perhaps if Hayashi-kun wants to think about it and later communicate with you over email.
Okay, thank you.
That should probably be.
No, thank you.
Okay, thanks a lot,
I'm sorry.
Sakurai-kun, for your. Oh no, not at all, not at all. So thanks a lot, Sakurai-kun, for your question, and Hayashi-kun, thanks a lot for your talk. It was a very nice and interesting talk.
Thank you very much.
Thank you. So I'll introduce the next speaker, Dr. Arjo. Hello, Arjo. How are you?
Hi, thanks. Nice to see you, Prasanna.
Yeah. So he'll be talking on non-equilibrium phenomena with dipolar gases in optical lattices. So Arjo.
Okay. Am I audible?
Yes, yes.
Perfect. Look a second. Okay. It's supposed to. Wait a second. Wait a second. I need to. I can't see. Okay, let me think. I need to stop share for a second. And perhaps directly here presentation. Yeah. Is it okay now?
Yes, yeah.
Yeah, so yeah, because the panel of all the picture of the videos were blocking my panel to select presentation mode. Okay, sorry for the small technical glitch, and thank you, Prasanna, for the introduction. It's nice to see you, and also thanks to the organizers for giving me the opportunity to talk in this very nice conference. Yeah, and today I'll be talking about our recent work on non-equilibrium phenomena with dipolar gases in optical lattices. And before I begin, definitely I want to wish Professor Das a very happy birthday. It was on 27th of June. This was the, I was like really, it was my pleasure and honor to have known him and worked with him at my PhD. This was the final. These are some pictures of him with me and others also. Like this is last day this is my last day in Institute of Astrophysics, and when Professor Das visited me in Frankfurt, and you can also see Buddhaditya visiting us in Frankfurt. Yeah, he was a real inspiration for me, not only in academia but also other aspects of life, and I cherish all the memories which I have spent with him. So my talk will have two parts. The first part would be on the quasi-localization of dipolar gases in one-dimensional lattices. And the second part of my talk would be on how to realize a Halder insulator phase, again, with polar gases in optical lattices. So to begin with, as we know that when a single quantum particle hops around in an infinite lattice with random on-site potentials, then this particle gets localized. And this is the famous single particle or Anderson localization. And this has been observed in various experiments, like in solid-state physics and also in ultra-cold gases. Now, what if we have interactions in this system with random disorder? So in this system's localization can also occur, although interactions and localization are sort of like counterintuitive. And this is called the many-body localization, and this has also been observed in cold gases. So the question which we intend to answer in this project was, in the absence of disorder, can there still be an effective localization with power law interactions or dipolar interactions, to be specific? Like, in other words, can the system at least partially remember the initial state after anomalously long times? Here what I mean is experimental times scales. So for this, we considered the following Hamiltonian of extended Bose-Hubbard model with hardcore bosons. That means we have the constraint that there can only be a maximum of one particle per lattice site. So the first term tells the hopping to nearest neighbor, and the second term is the dipolar interaction between atoms situated at sites I and J. So now, suppose if we have two atoms in neighboring sites, so they can form a stable nearest neighbor dimer if the interaction strength is very large. And a simple two-particle calculation show that this nearest neighbor dimer can remain dynamically bound for interaction strength larger than 7 times the hopping. And this will also lead to a quasi-conservation of the number of nearest neighbor links between these two atoms. And how can this nearest neighbor dimer hop? Well, it can hop through a second-order process. And second-order perturbation theory tells that the hopping amplitude of a so be careful, this is JD, not the hopping amplitude of a single particle. So JD is given by J squared over the interaction strength V. So the first particle hops and the second particle follows. This is something similar to the repulsive bound pair, which comes up in the Bose-Hubbard model, that is just interaction, and then just the hopping and on-site interaction. And when the on-site interaction is very large, then the repulsive bound pair is dynamically stable. Now, suppose if we have more than one dimer, like say 2 dimers separated by a distance n. So there are 2 energy scales which are competing. One is the hopping of the dimers given by JD, and the other is the dipolar interaction between these 2 dimers given by VD. So when these energy scales sort of become comparable, then these 2 dimers become stable and they become dynamically bound. And the critical separation is given by this relation, which is a power law, and V over J to the power of 2/3. And indeed, our numerical simulations show that this critical separation follows this power law when we have just 2 dimers. So when interaction strength, dipole interaction strength between the dimers is much more than the hopping of the dimers, then the bandwidth of the dimers cannot accommodate the kinetic energy which is released when the dimer is broken apart. This is something similar to repulsive bound pairs. However, we wanted to see a bit more of the dynamics of these dimers, how the system evolves. And for that, we looked at the Shannon entropy. And so for an unbound nearest neighbor dimer, since it's not bound anymore, the maximum entropy it can have is twice the log of the number of sites in the system. And if the nearest neighbor dimers are bound, then the maximum entropy is given almost by log of the number of sites. So here we see 2 dimers separated by 5 sites. And for a smaller value of interaction strength, we see that the entropy increases very rapidly and almost reaches the maximum value, expected maximum value. Whereas when interaction strength is very large, the entropy increases very slowly, and only at later times when through the center of motion of these cluster will the entropy increase and saturate in the expected value. So now if we add more nearest neighbor dimers, what happens? Well, adding each additional dimer increases the homogenization time exponentially. That means the time needed to homogenize for the system for the atoms to expand in the entire lattice. However, one should keep in mind that the nearest neighbor dimer positions need not be periodic. That means as long as the separation between each dimers is smaller than the critical separation for that interaction strength, the entire system freezes out. So although these results are for one dimension, the dimer-dimer bonding is valid in any dimension. Now, what if we put one single particle between these 2 dimers? The single particle experiences a box-like potential and it delocalizes between these 2 dimers. If the interaction strength is very large and the single particle cannot escape through a swap process, however, still conserving the number of nearest neighbor links, which I mentioned in the very beginning. So any motion of the dimers will change the singleton energy, and hence the dimer motion is not only constrained by the inter-dimer-dimer interaction, but also change in the singleton energy. So this is a numerical simulation of initially 2 dimers separated by 15 sites and with a single particle in between, and the interaction strength is 50. And we see with time, the single particle delocalizes between these 2 dimers, but these 2 dimers remain as they were. And we should keep in mind that the density is very low. And for this interaction strength, this leads to a quasi-localization via massive dimer clustering. So these values of interaction strength is possible in current experiments with magnetic atoms and molecules. So now let's just compare the critical separation needed for this cluster formation as a function of interaction strength. So when we have just 2 dimers and when we have 2 dimers with a single particle. So both of these systems follow the same power law behavior, but the pre-factor gets increased almost by a factor of 3. So now let us think about a different system where we have a box-like potential and we throw in some dipolar atoms in this box, and the density in the film factor can be less than 1. What happens when we remove this box potential? Will this cloud remain self-bound or will it expand in the underlying lattice? And the answer depends on 2 things, the interaction strength and the filling factor. And we can actually have a phase diagram for it. where in this gray region, the system will remain as a self-bound lattice droplet. One thing we should keep in mind that these droplets are not just moth-like filaments. So there are the density can be less than 1, and that means that there are holes or empty sites which are mobile but confined within. So for density 1, the critical interaction strength is around 2.5, which is possible in experiments with erbium. So the conclusions from the part 1, let me not go through it since there's a time constraint. Let me now go to the second part of my talk, that is to realize Halden insulator. Halden insulator is a paradigmatic example of a symmetry-protected topological phase. It is exhibited by Heisenberg model with odd integer spin in 1 dimension. And it is unique gapped ground state in the bulk with unpaired spin halves dangling in the edges for open boundary conditions. And it has several symmetries. So, so we wanted to see how it can realize in experiments, and we looked at the extended Bose-Hubbard model, which had hopping, and between nearest neighbors, we have dipolar interaction, and we also have the onset interaction. And here we are taking soft core bosons. So now we can, in the simulations, we considered almost 5 maximum number of particles per site. So just with nearest neighbor interactions, it was observed that the phase diagram shows many phases: the Mott insulator phase, the density wave phase, and sandwiched between these two phases is the Halden insulator phase. And this is at filling factor 1. And this Halden insulator phase is characterized by the string order, where delta n is the difference between the occupation at site I from the filling factor. So in experiments, one can easily prepare a Mott insulator state and density wave state. But then when we quench to the Halden insulator, it will pass to this quantum critical point, and that will definitely create defects. And so we not get a perfect or a very good Halden insulator. So to reduce the defects, we wanted to see if we find the best quench protocol or a recipe for the experimentalists. And then we found out that the best way to do it is the initial and starting point should have overlapping insulating lobes. And that's how we found out that to go from Mott to Halden insulator, we should change both U and V, whereas from charge density wave to Halden insulator, we can just change V. And then we looked at the fidelity with the final state in the Halden insulator, and we see that when we go from the Mott to the Halden insulator, the fidelity with the ground state is above 98% for quench times, for linear quenches with quench times more than 10. Whereas for charge density wave to Halden insulator, it barely reaches 70%. And the reason can be given through Kibble-Zurich arguments. However, so in experiments, it's difficult to prepare a very good ground state, the exact ground state, initial ground state. So we thought of let us put some excitations in the initial state so that it can have some defects or so, yeah. And so we quenched, what we did was we suddenly quenched it to some other points inside the Mott insulator, brought it back, and then we did this linear quench to Halden insulator. What we saw was that the string order is quite robust against initial excitation. So we gave excitation energies of the order of almost 30% to the initial ground state energy. And we saw that for all of them, the string order were almost similar and very close to the ground state string order parameter in the Halden insulator. Yeah, so this is the conclusions that dipolar strength needed to achieve Halden insulator is reachable using infinite atoms. And it is better to start from the Mott insulator side and quench it to Halden insulator according to the protocol described. And the string order is quite robust against initial excitations. So yeah, thank you. And let me also wish Professor Das all the best for his new journey and hope he never retires. Thank you.
Thanks a lot, Arjo, for your very energetic talk. So there's a question from Professor Bimalendu there. He asks, how can you engineer power law NN interaction between neutral atoms?
So by using magnetic atoms. So we can use the magnetic dipolar interactions. So for example, erbium or dysprosium. So for example, I think in my last slide, I already have some examples. So like for example, sorry, this is 166 ER. So we can already get interaction strength of 2.7. So yeah, these are like magnetic atoms. So now these are not electric type interaction, but magnetic type interactions.
Okay, thank you. If there are no more questions, then I'll thank Arjo for his talk. It was nice having you here. Thanks.
Thank you.
Yeah.
Hope to talk to you soon.
Yes, sure. Thank you. And I'll now, the next speaker is Dr. Geeta, and she'll be talking on data-driven model for anomaly detection, case studies from oil and gas applications. Okay.
Can you see my screen?
Yes.
Yes. Can you hear us? Everyone hears me also. Yeah.
Yeah.
Thank you. Thank you. Hello. Good evening, everyone. Actually, this is it's almost 5:15 here in here. 1 minute. Let me. I have some. Okay, there it goes. Okay. Thank you, the organizers, Professor Mukherjee, Professor Vijaya, and Prasanna for the opportunity to be part of this Professor Das 65th birthday celebration and giving me a chance to present what I am working now in the industry. I know this topic seems to be a very much an outlier in this conference, and but I would like to use this chance to demonstrate how I have used what I've learned under the guidance of Professor Das during my doctorate work, which you will see that it will fit very well into this kind of conference. So the field of atomic physics, if you look at it, it relies on experiments and simulations-based models to understand the physics of different atoms and interactions among the basic building blocks. So that's what most of us are talking about it so far. So as a physics-driven modeling scientist, one looks at first principles like hypotheses and theoretical formulations and equations, which are already created by well-known scientists, and we add more additional theoretical formulations, and we create an analytical model. So with the advent of computers, what we did was we took these analytical models and we tried to solve it using numerical methods to a very high accuracy. And in my case, it was like high accuracy atomic wave functions, and a lot of the previous speakers were talking about that. Once I had these good, highly accurate atomic wave functions, what we went ahead in doing was to calculate further properties like ionization potential, hyperfine constant, which were compared with the available experiments for the validity to compute the quantity which we needed, which is the E1 PNC, which was for electrical dipole transition amplitude due to E1 PNC. So basically, this is what my PhD was. This was like a flow in which it worked. And now coming to the data-driven modeling, what actually happened was I start with available historical data, and I understand the patterns in the data using various exploratory methods and in discussion with basically the subject matter experts or physics-driven scientists. So in my case, I am in a new place where I don't know anything about geology or geophysics or anything. So what I try to do is I do that first part is where I work with physics-driven scientists and I get the idea from them. And once I have a clear understanding of the dependent and independent features of the problem from the data, my job is to find a function which connects them. That is what is called as patterns. That is basically what people call as patterns in data science terminology. And once I have a pattern, I can create a model out of it. And I can do that just like at very different levels of approximation. For example, in our case, in atomic physics, we tried something like MP2 or CPHF or CC, couple of cluster methods and so on. So here, the data-driven approach, we go from ML, machine learning, to kind of a deep learning methods, where I try to do to reach close to AI kind of results in this industry 4.0 digitalization area. So you can see that both these seemingly unrelated but very intimately connected fields merge in a seamless and very synergetic manner, only with the blocks moving to different places. So I hope I have made it, at least I try to convince that I'm Professor Das' student. So what is Industry 4.0? So this is just to say that it's just an introduction so that it will flow in along with my work, what I'm doing. So we know that first three industrial revolutions were powered by steam, electricity, and computers in this chronological order. Now we are in the 20th century where we are riding the 4.0 digitalization wave, which is basically fueled by data and artificial intelligence. So in this space, we heavily focus on this interconnectivity, automation, and so on. And the company where I'm working now Halliburton, which is a service company, which is a hydrocarbon life cycle company. They are embracing these Industry 4.0 standards. So that's where I am, and I work on some of these subjects related to that. Okay, so what do these oil and gas companies use data for, and where is this data coming from? So there is a huge, staggering kind of amount of data which comes from drilling to production of hydrocarbons. And there are complex operations which are run by engineers very well versed in different fields, like starting from geophysics all the way to flow dynamics and so on. So there are enough number of PhDs who are working on pure data, physics-driven work there. So the primary task associated with oil companies in the hydrocarbon is the hydrocarbon exploration. So need to first find out where the oil is. So basically, you look at improved subsurface characterization using seismic or even bed boundary, fault locations, and porosity and lithology kind of data, and fluid phase and contacts and so on. So I don't work on any of them. I just get the data and I look at it in a very different way instead of looking through the similar way which I used to do it previously. So these are vital information on planning where to prepare a drilling well. And once we know where the drill is, we need to drill the well. So again, drilling well is also again a cumbersome and very physics-driven part, like where you have to know what is the torque of the drill bit and so on. So there again, it's a complex phenomena which almost a digital rig kind of 1 to terabytes of a day, 1 to 2 terabytes per day of data is collected from around 60 sensors at a very high frequency. So we are talking about time series analysis there, where we use Fourier transforms and to convert it into different kinds of features and so on. So once we know, okay, we have done the drilling, so what is the next point? Where we need to bring this oil back into the subsurface. So there you need to have several pumps which are used for artificially lifting these hydrocarbons. So there again, you are trying to learn about how a predictive maintenance of different kinds of pumps and so on. And in addition, there are lots of unstructured data which is created by these subject matter experts. So unstructured, I mean the text related, like so much of content is there in the text. So we need to bring out that information into automation. So that's where natural language processing comes in. And I'm very much involved in a lot of natural language processing techniques with some of the customers. So, and then we have this asset surveillance and health and safety and so on. I can go on, and there are lots of data which comes in through this. So let me come to this I took a very simple case because of the time constraint, and I'll talk about the simple work which we did for an oil company in the Middle East, where our objective was to find out the anomalies and how can we identify that, and it was for some of the pumps which are running in their field. So we know that anomaly detection is nothing but rare events, just identification of rare events or observation. And I am an outlier in this conference in a way. So how can we identify that? So the first thing which we can think about is just plot them, just start plotting between two variables. So if you have just 2 variables, you can plot it as a scatter plot. What about if it is 3, 4, and so on, and it goes as n square, and it's very clear it's not possible to do that way. So we need to find a method in which we could reduce this dimension. That's where we come up with these 2 approaches, where one is an unsupervised approach. Don't worry about that, where the model is just given all features without any distinction of dependent and independent features, and it is asked to try to find a pattern hidden inside them. And the next one is a very semi-supervised approach, where part of the training is done with just data, which humans have looked carefully and labeled it as normal, and the rest of the portions are used for testing. So in all the machine learning approaches, we have partly a trained data and a test data. So it will become much more easier. I hope in this audience, I'm sure you might have read about all these new developments which are in data science. So I don't want to bore you with all these stuff. So it's an expensive, the semi-supervised approach is an expensive approach because you need to have the domain expert looking through this huge amount of data, and they need to label them. But in terms of accuracy, semi-supervised or supervised semi-supervised or supervised approaches are better, as we check the error prediction validity with result gives a better one. And let me first look at the first approach, which is called the principal component analysis. I'm sure every one of you in this audience would have done something on SVD and other kinds of methods. And this is one kind of method where what we are trying to do is we are trying to reduce the whole amount of variables that are collected from sensors to reduce into a smaller or lower dimension. It's a very simple approach. What we are trying to do is every variables, there might be correlation between them. So you don't want two correlated variables to be there. You want to reduce it into, instead of two, we need it to be reduced to one. So basically by doing that, this approach looks at a large amount of variables and then reduce it into a smaller dimension where it can, each of these features can be really be the only features required to explain the variation in the data. Okay, so usually using further visualization on the same in lower dimensions usually brings out the pattern inside the data in the form of clustering. Basically, and thereby we can easily find out what is an outlier or an anomaly in the data. So this approach makes it very but the one just problem is this approach makes a assumption that all the features are linearly dependent to each other. So it's like a Dirac-Fock method for our case, like it's a starting point. Okay, now coming to this next approach, if you look at it, that's a very well-known method, and you might have heard of neural networks and so on. So to understand neural network, auto-encoder a neural network, we need to know what is a neural network is. So in simple terms, it's like a computer architecture in which a number of processors are interconnected in a manner suggestive to the connections between neurons in the human brain. Okay, and you basically try to find out the weights and bias by the process of trial and error. And that's the same thing which we have done it for example, configuration interaction method. We try to find out what is the C values, the coefficients and so on by putting constraints on some of them. So and we always optimize these things. And the autoencoder is a kind of a neural network with a specific architecture with the number of neurons in the input layer and the output layer exactly same. So that's the only thing. The usual neural network, it's not a must. That input layer and output layer can be of different numbers. So, and it performs two tasks. As you can see that, as I said in the previous approach, PC also reduces the dimension. Here also, what it does is it takes the input and it compresses the data to a lower dimension. And you can see that the encoder part, it's becoming smaller. From 4, it becomes 3, and then it becomes 2. That means you basically reduce the number of dimensions to 2. And in the second part of the data, what we are trying to do is we reconstruct it back to the same dimension. And while reconstructing, you actually do it. You bring it back like a backward propagation. You use backward propagation to find out what is the change in the value, which is, basically you do a back propagation to so that we minimize the prediction error. So the first part is called the encoder, and the second part is called as the decoder. So it is exact. If I can tell you, this have lot of resemblance to what we have done in CI method, exactly solving the coefficients and so on. You do a continuous solving of the equations till you get the consistency. So in autoencoder anomaly detection workflow, as I said, we start we decide the layers, the number of activation functions and optimizers and all those things. We can change it depending on, these are hyperparameters, which we can optimize it further. And you fit the model with the trained data, which is already labeled by an expert. And you continuously do this looping and make sure that you try to find out the reconstruction error. And so you are sure that if any new data when it comes in, and if this error is above a threshold, that means you flag it as an anomaly. And this is a great, easy, simple approach, but it's very easy to understand also. And thanks to Professor Billy, my senior, who helped me. I'm sure he is in the audience, and in the initial years teaching me photon as well as conjugate gradient method. You remember that? So we exactly use gradient descent here. So if you see this, any of this reading about data science, they talk about gradient method, and we used it sometime years back. And I always think about you for the kind of learning which I've got from each of you. And using, so I hope I made you understand like kind of what is that we are doing. But and one more additional point is, the most important point is that these neural network architecture, due to the nonlinear activation functions, actually it is able to take about nonlinear interaction between features. So you can see that it is going as an higher order. It is trying to see the higher order interactions between these features. So
Dr.
I'll
Geeta,
just direct. Yeah.
Sorry, you have about a minute left roughly. So
Yeah, it's done. Thank you. So in the first approach, you can, I just used a first approach where we get, in this graph, what you're seeing is the result from one pump from which we got almost 400 sensor variables, out of which 1/4 of it were biweekly variables, which is low frequency variables, and rest of them were at a very high frequency, like in every minute. So the original failure date of this pump was marked on September 10th. Okay, let's say that. So we want to see something before that, so that they can do some kind of remedial operations. That is what was our objective. So we did PCA on this, and you can see that PCA couldn't pick up all these interactions between these so much complex operations going on in that. So we couldn't get much, but you can see that it was showing that in this green curve is our threshold, which is calculated from our PCA result. And this was the original value, the combined variability, which is going closer to the threshold, and it's crossing the threshold after the failure date. So basically we couldn't catch the whole thing. Whereas with the autoencoder neural network, you can see that it takes care of this nonlinear interaction, and you can see how it predicted the failure and give alarm for the data almost 2 months ahead. So this was a really a very simple method which we could show value from these data. So to summarize, we looked at 2 approaches for anomaly detection, and we understand that the autoencoder neural network are best candidates for this work, for production level workflows. So thank you for the attention, and if you have any questions, I'll be happy to answer them. Thank you.
Okay, thanks a lot for your nice talk. So there are a couple of questions, but in the interest of time, I will probably skip it. But Professor Das has written a comment which I'll read out.
Okay, sure.
Yeah, so he says, thank you for your explaining the connection between your PhD work on atomic physics and your present work on data science in a clear and concise way. I look forward to learning more from you on data science in the future.
Oh, thank you, sir. I am always your student, and I think I am going to learn more from you. Thank you. Thank you.
Thank you. There are a couple of questions, one from Ritvik and other from Arjo. So I would request them to email the questions to Dr. Geeta.
Sure.
Okay, thanks a lot for coming and for this nice talk. Thanks.
Yeah.
Yes. Our next speaker is Rene Viella. He's going to speak on fine structure splitting of boron-like atomic systems using the VQE algorithm. Okay.
Okay. Can you hear me and see me?
Yeah, yes.
Okay, can you see my screen?
Yes.
Okay, so good evening, everyone. Today, I would like to briefly introduce the problem that I've been working on with Professor Das lately, which is the fine structure splitting of boron-like atomic systems using the VQE algorithm. And first, some context, although quantum hardware is here, it is in a very fragile state. It is very susceptible to noise and decoherence problems. And although in theory there are error correction codes, these require too many resources. For comparison, in this photo, we have Google's Sycamore quantum processor. I'm not entirely sure if it's the world's most powerful quantum processor, but this one has 54 qubits. And error correction codes for the kinds of problems in quantum chemistry require between hundreds or thousands of qubits to protect the information of a single qubit. So this approach is not viable now or in the foreseeable future. So instead, we refer to the paradigm known as noisy intermediate scale quantum computing, in which the methods and techniques applied there require little to no error correction whatsoever in order to give some accurate results. And one such example is the VQE, or variational quantum eigensolver algorithm. The general idea is to minimize the amount of quantum computation used in these methods in order to reduce to the minimum the influence from the coherence and those noise problems. And what the VQE does, it is a hybrid algorithm in the sense that it has some steps performed on a quantum computer and some other steps performed on a classical computer. So we start with a fermionic problem or any quantum chemistry problem. And we first map the Hamiltonian, the expression that describes the energy of the problem, into second quantized form in terms of creation and annihilation operators. And then we need to use a mapping to map those creation and annihilation operators into qubits, operations that the quantum processor can handle. So these creation and annihilation operators get represented by these Pauli strings, which are a series of Pauli matrices. And we also need to choose an ansatz. It can be a physically inspired ansatz like the unitary couple cluster, or can be hardware efficient ansatz. It really depends on the problem. So the steps of the VQE algorithm are as follows. We choose the ansatz and a set of initial parameters to prepare the trial state, an initial trial state in a quantum computer. Then using in the same quantum computer, we measure expectation values of the Pauli matrices that are related to the Hamiltonian of the problem. Then in a classical computer, we calculate the energy using the Hamiltonian coefficients from the problem using the 1 and 2 body integrals. And then if the energy is not within desired accuracy, we adjust the set of parameters and iterate this process until we get a suitable set of parameters that would solve our problem. And the good thing about the VQ algorithm is that further error mitigation techniques can be applied. For example, the Richardson extrapolation, in which we intentionally adjust the amount of noise in the problem and conduct several experiments for several values of the noise. And then using the data points, we can extrapolate it to what the noiseless value would be in theory. And although the VQ algorithm is usually applied to get ground state energies of atoms and molecules, we would like to extend its application for the problem in question, which is the fine structure of boron. In brief, the fine structure is the splitting of energy levels in atoms due to relativistic effects, in particular due to the dependence of the energy on the spin of the angular momentum of the atom. And what makes boron a good system to study is that it has a 2p electron in its ground state. We don't see a fine structure splitting in the 2s electron, but we do see a fine structure splitting in the 2p shell between the 2p 1/2 and 2p 3/2 electron. And in order to get good Hamiltonian coefficients and a good trial state, for the ansatz of the problem, we have chosen to use the relativistic unitary couple cluster method, which is based on the virtual excitations of the Dirac-Fock method in its Dirac-Fock state. But why can we apply the variational quantum Eigen-Solver algorithm for the 2p 3/2 states? Well, we have a variational principle for excited states as well. The usual variational principle states that if phi is a trial wave function, then assuming that it's normalized, this expectation value is greater or equal than the ground state energy. However, if we consider a state that is orthogonal to the actual ground state or to a state that is sufficiently close to it, then it can be shown that this expectation value is greater or equal than a higher energy eigenstate. Since angular momentum eigenstates are orthonormal, this is a good quality or feature to use. And this can be applied to the 2p state with angular momentum equals to 3/2. In some sense, we can say that the 2p 3/2 state is the lowest energy state for this particular angular momentum, and hence that's why we can apply the variational principle. And this is an ongoing project, but the main statement of the problem would be that. And I would like to also dedicate a few moments of this opportunity to talk about Professor Das. Unfortunately, I don't have any photos with Professor Das due to the COVID situation and everything. And in fact, I'm not in Japan at the moment. But I happen to have taken this photo of him. This was during the research group's presentation at the Tokyo Institute of Technology. And back then, I didn't really know much about Professor Das. I knew that he was part of the physics department, but he wasn't really accepting undergraduate students before, so I didn't know much about him. But as you can see in the slides in this presentation, he was explaining about the unitary coupled cluster wave function and the VQE algorithm. So after the presentation, I thought it was really interesting. And actually, we actually met at his office. We had a nice discussion. And what I can say is that he has been extremely supportive from the very beginning, always open for discussion. And I can say that he deeply cares for the progress of his students. Sometimes I even feel that he cares more about our progress than, well, maybe myself even. And he's always open for discussion, not only about the project, but physics in general, life, and it's always inspiring to listen to his anecdotes. And it's funny when I tell him things like, oh, I've been looking into this place for my graduate program, and then he says something like, I think nothing about me would surprise you by now, but I actually visited that place a few years ago and met this person who ended up winning whatever prize in physics for his or her discoveries. And I appreciate him because he's very humble despite being, well, the great scientist that he is. And for me, it's an honor and a privilege being here today and being a small part of this huge community that is Professor Das's community. And I want to wish him a happy birthday, best wishes, and all the best in his future endeavors. So thank you.
Thanks a lot, Rene, for that very nice talk and sharing your thoughts about Professor Das. So with this, we come to the end of the contributing speakers session. And I'll thank all the speakers who gave their talks and shared their thoughts and their associations with Professor Das. I'll hand it over to Dr. Bindi Arora now, who will take over. Thank you.
Thank you, Dr. Prasanna. Thanks a lot for chairing the session. And we are actually at the end of all the scientific talks now. And I think the conference was a big success, and we had a wide range of topics covered in past 4 days. We had very informative talks on fundamental interactions with atomic systems, including parity conservation, CP violation, searches for new physics. Also, it was discussed how to detect dark matter using atomic systems. We also had interesting talks on atomic clocks using highly charged ions and neutral atoms. There were talks which discussed on how to make quantum networks using artificial atoms, probing electron dynamics in the attosecond time scale, studying isotope shifts, and finding out nuclear radii of exotic atoms and molecules. So discussion on measuring EDM using atomic clocks was very interesting. A number of talks on development of atomic structure calculations and their applications were also presented. A couple of talks also discussed the quantum chemistry calculations on quantum computers, and there were few which talked about quantum communication and information. So talks exchanging ideas, the new ideas for development of experiments for high precision studies, they were very encouraging. So in all, we had a complete package, I think, in last 4 days. And before we close the scientific session, I would like to announce our winners for the poster session. And I would like to acknowledge TCG Chris for sponsoring our posters for top 3 presentees. Without any further delays, I request Professor Das to announce these awards.
Okay, so can you hear me?
Yes, we can hear you.
So I'll announce the winners for the poster presentation. The first position goes to Jyoti, and
Yeah, please. Sorry, go ahead, Professor Das.
Okay.
Yes, sure. Sorry.
And for a presentation on the magic wavelengths for excited states, transitions in rubidium and cesium for optical lattice-based active clocks. And she's from Guru Nanak Dev University, Amritsar.
I am unable to share. Yeah. Right. Do you all see my screen?
Yeah.
Yes, but it's slightly lower volume, maybe.
Okay. Shall I continue? Okay.
Yes, please.
Okay. Now the second position is Yatin Batra. The title is Probing the Chemical Applications of Light and Matter Interactions. And he's also from Guru Nanak Dev University, Amritsar. Okay, the third position goes to Arpita Das, and the title is Coherent Control of the Optical Faraday Rotation, and she's from Shah Institute of Nuclear Physics in Kolkata.
Thank you so much, Professor Das. Thanks a lot. And I congratulate all the winners and the other participants as well. With this, we have come to an end to the scientific session. I would request Professor Prasanna to kindly present a vote of thanks.
Okay. So, yes, sorry about that. Yeah. Okay, so thank you, Dr. Bindya. I'll first thank PRL and Cyrox for making this event so successful. And of course, none of this would have been possible without the organizers, including the students from the Cyrox club. I also wish to thank TCG Crest for sponsoring the posters. Last but not least, Professor Das, of course, deserves a big thanks for inspiring so many of us and making this conference possible. And before I hand over the proceedings back to Dr. Bindya Arora, I will apologize in case I've inadvertently left out someone. Thank you.
Okay. Thank you, Dr. Prasanna. Thanks a lot. We would now like to proceed with the felicitation ceremony. And those who want to leave the session, they are free to do so because the scientific session has already ended. And those who want to stay back with us are most welcome.